Max experiments at large.
Science Max!
Gravity.
Gravity!
Gravity. Gravity makes things fall. But on this episode, I'm doing everything I can to defy gravity.
You win this one, Gravity.
From a hoop glider to an egg drop to a hover balloon, it's a gravity-defying dance party. All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max, we're going to be looking at gravity. What goes up must come down. Today, gravity is the force that makes things fall towards the ground. But just because it's a force of nature doesn't mean that we have to listen to it. No! Today on Science Max Experiments at Large, we're going to use everything in the power of science to defy gravity. We are going to be making a hoop glider. Now, hoop gliders may not look like much, but they fly just like paper airplanes. Woohoo! And here's how you can make a hoop glider. Here's how you can make a hoop glider all your own. This is what you need. Index cards, scissors, straw, ruler, pencil, and of course, science tape, which is just like regular tape, except you use this kind of tape for science. So, here's how you do it. Take your index card and cut it into 3 equal lengths. Take 2 strips, and you take your science tape, and you tape those 2 strips and make a hoop out of it. And with the small strip, you want to make another hoop. Now, what you want to do is take your straw. Now, this straw has a little scoop at the end, and that's not very aerodynamic, so we're going to get rid of that. Ooh, maybe it was kind of aerodynamic. All right, now that we've got the straw, you have to align the hoop and the straw together. So here's what I like to do. Take some science tape and stick it on the straw, and then align it so that it's perfectly straight, and then stick it on. Looks straight to me, all right? The small hoop also has to be perfectly aligned with the first hoop. So again, put the tape on the straw first, then align them up, and then start looking down through it to make sure it's aligned. There. Once you have it all taped together, you're done your hoop glider. And it flies just like a paper airplane. Pew! Awesome. So that's what we're gonna do today. Oh yeah, I gotta clean that up. We're going to max out the hoop glider. I'm gonna go meet Sonia at the Ontario Science Center, and we are going to max out the hoop glider into a giant version. We'll probably have to change the materials we use because, I don't think we can get a straw that big or cardboard, but still, we can figure it out. All right, here I go. Aha!
Oh, hi, Phil. Yeah, what? Pardon? You want me to help you with an experiment? Okay. All right.
Oh, Sonia, I came in.
Phil,
You came in here? I
Are
came
you
in.
okay? Are you okay?
Yeah, I'm fine. Come on, let me show you. This is what I would like to max out. It was in my pocket when I fell, so
What is that?
It's a hoop glider. It was a hoop glider. So how do we max this out?
First, we're gonna need a larger tube.
To replace the straw, yeah.
Exactly, and we're gonna need 2 hoops. So we need something that's flexible that will convert into a hoop.
Okay, that's great. So why don't we get started?
Sounds good.
All right, high fives. You may recognize this. It is a spring. Yes, good for you. But did you know that springs can defy gravity? Whoa! Gravity defy. Gravity defy. Gravity. Look at it fly! defying. Okay, not exactly, but what if I was to hold the spring like this and let it go? What'll happen? It'll fall. Yes, it'll fall. That is true. But while it's falling, what happens to this end? Does it stay in one place? Does it go up? Or does it go down? Let's find out. I'll bring this in so you can really see it. Okay, ready? Watch close. Did you see? Did you? No? Okay, tell you what. We'll watch it again, this time in slow motion. See? The bottom doesn't move, and here's why.
When the top of the spring is released, gravity and the tension of the spring are pulling on it. The bottom of the spring is being pulled down by gravity and up by the tension of the spring. These forces cancel out, stopping the bottom of the spring from falling until the top reaches it.
Until there's no more tension, and then the top passes the bottom and the whole thing. That is how it works. But here is the real question.
Will it happen differently with a longer spring? Huh? Well, I just happen to have a longer spring!
Let's max it out! Bring it. Don't tangle it. So, now that I'm up high on this fire escape, let's test it out. Okay, 3, 2, 1, go!
A longer spring still has the same forces working on it. The tension of the spring pulling it up and gravity pulling it down. No matter what size of spring, these forces cancel out for the bottom of the spring until the top meets up with it.
So there you go, an almost gravity-defying spring! Hey, there's no door handle on this door. I guess I have to take the stairs. Whoa.
Sonia and I are maxing out the hoop glider out of bigger and better materials.
This is the largest tube I have, right?
A giant ABS pipe and some bendable metal to make into hoops. Then we attach them all together and...
Okay, big hoop is done.
And little hoop is also done.
Awesome.
Not bad.
Not bad at all. Super solid.
And that's the thing. We have pretty heavy material, so it might not fly as well as we'd like.
But something heavy can always be good, right?
Oh no.
That's what I'm talking about. See how solid it is?
Pretty
No
solid.
damage whatsoever. You want to test it?
I think we should.
Okay. I'm excited.
we take our plastic and metal hoop glider outside to test it and...
Ready?
Ready?
1, 2, 3!
Huh.
It didn't really fly, did it?
Sonia and I made a very solid design, but the problem with it became pretty obvious.
Yeah.
It's just too heavy.
Well, that's what science is. Back to the drawing board. Here's something fun you can do if you ever get your hands on a helium balloon. Now, helium balloons float up, not because they defy gravity, but because they're lighter than air. It's because the heavier air around it actually falls past the balloon, and that ends up pushing the balloon up. But what if this helium balloon wasn't lighter than air or heavier than air? It was exactly the same. This is what I like to do. Just take a helium balloon with a long ribbon and a bunch of paper clips, and adding a little bit of weight every time. And what we want to do is make this balloon neutrally buoyant. That means it won't go up or down, but it will be neutral. You want to check it every once in a while. Let's see, 3 paper clips is clearly not enough. 5 paper clips is, 5 paper clips is pretty close. It still might float down, so you want to take off just a little bit of weight, maybe about there. Watch this. You just take the balloon and you put it somewhere and it stays. It stays put. It doesn't go up. It doesn't go down. It's attached to nothing. Now, let's max it out. I had a big balloon and it was there. a giant balloon. And look, it's a great paper towel delivery device. Say, did you want some paper towel? Here you go. Science. Yeah, don't worry about Ramona. Just put them up high. Put them up, yeah, higher. Good. Hey. Grab it. Grab it. Gravity makes things fall. But where do they fall? They fall down. Oh. Towards the center of the Earth. Eh? Gravity. It fell, didn't it? So, the Earth causes gravity, right? Well, yes. Gravity. Oh, come on. Everything that has mass has gravity. Gravity. But the Earth has so much mass that the gravity produced by everything else is like nothing. I mean, forget about it. But let's say I was in space with this chicken. I would have gravity, and I could exert a gravitational force on this chicken. And if I get my angles right, I might be able to get the chicken to orbit me, like a moon. Behold, my chicken moon, huh? Gravity. But let's get serious. What causes gravity? We don't know. What we do know is that without gravity, there would be no universe as we know it. No you, no me, no chicken moon. I'd miss my chicken moon. Chicken moon, you what? Gravity. Like it or not, the universe wouldn't exist without it. You like the sign? I'll give you a good deal. Half off.
Back to our hoop glider, which was too heavy.
Here's what I don't get. This is heavy, but I can still pick it up and throw it.
Yeah.
An airplane is way heavier. I could never pick up an airplane, but that can fly.
And that's because airplanes have engines, so it has a constant source of thrust. When we throw it, we just have an initial source of thrust. So we're throwing it, eventually loses its energy, therefore
It falls to the ground.
it
I
falls.
see.
So we need something that's light.
Light.
And something that's strong.
And strong. Okay, well, let's see what we can find.
All right.
Sonia and I try a plastic tube and some heavy-duty paper. We make hoops and attach them with some duct tape and run outside to try it out.
Hoop glider dance! Okay, 3, 2, 1.
That's pretty good.
That was
Pretty
amazing.
good.
Let's try that again.
Here we go.
I throw the hoop glider, and although it doesn't keep flying forever, it goes much further than our first version, and also further than I could have just thrown the pipe by itself.
Pretty good.
So we've done a good job of making something that flies. Why don't we make a couple different kinds out of different materials, and we'll see if we can get one that flies even better than this.
I think that's a good idea.
Yeah, okay, let's do it.
Sonia and I have created a pretty good maxed out hoop glider, but we wanted to see if different materials would make an even better one. Sonia made a much lighter version,
This time I used cardboard.
and I
made this!
made a slightly heavier one.
Let's do it.
Okay, 3,
Yeah.
2, 1, go! Not bad. My turn.
Here we go.
Okay. Yeah. That didn't really go very far at all, did it?
No.
Okay, so now we can measure it against the one that we threw before.
And
to see,
that went pretty far.
This went pretty far to see if we've got a better design here.
Here we go.
Right?
Awesome.
So, heavy one, no. Light one, no. Interesting.
No.
This design seems to be the best one. I keep thinking about how you were talking about thrust.
Yep.
All the thrust that we can put in is just what we can put in with one throw.
Yeah.
What if we could give it more thrust than that?
How can we do that?
I don't know, like some sort of slingshot or something. Like it'd have to be a pretty big slingshot.
A pretty big slingshot.
Do you
But I
we can
think
make
that sounds great, though.
I think make a big slingshot for this?
Why not?
Okay, high five. Let's do it. This is an egg. Eggs do not like to be dropped. Oh, fortunately, we can use the power of science to design something that'll keep the egg safe as it falls. Behold, my egg drop contraptions. The thing I really like about this experiment is there's no wrong way to do this. You can come up with any design you want and see if it works. This one here is a bunch of helium balloons. This structure is just to keep the helium balloons on so the egg can touch down very gently. Here it goes. Whoa. and the egg is unharmed, miraculously sound. That one worked really well. Success. This is a giant helium balloon that I think will work pretty much the same way, because I think this balloon will drop just slowly enough that the egg can actually just touch and nothing will happen. So that didn't work. And then there's this one, which has no slowing at all. It's all designed to just absorb the impact. And the idea is that the cone will crumple and absorb the force when it hits the bottom. Oh, no! Oh, no. I think it would have worked if it hadn't turned in the air, but it did, and, well, I guess the egg is completely broken. So I'd call that one a fail. This one is the parachute. You see the egg has been nestled into this foam container, and this is a parachute that will hopefully slow the egg down. Woo! Uh-oh. Whoa. Over. Good. And that one seemed to work well. Yep, the egg is totally fine. The parachute worked. All right, egg drop experiment, totally fun experiment to do, but the question is, how do we max it out? And the answer is pumpkin drop. Same thing, except with a pumpkin instead of an egg. Come on. Okay. All right, pumpkin drop with everything attached all at once. Okay, here we go. Ready? 1, 2, 3. So what we've learned from this is the heavier something is, the more force is acting on it from gravity, which means the harder it is to slow down when it's falling. Okay, fair enough. You win this one, gravity, but I'll beat you next time. I'm gonna get a broom.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. Delicious. Nothing is more important to have fresh than your seafood. It's what makes the difference between a fresh fish and one that isn't so fresh. If you live by the ocean, you probably know that the water gets high tide and low tide. Look closely, it's the same location. Amazing. But did you know that this is caused by the gravity of the moon and the sun? See, this cookie is the Earth. And this little happy fellow is me. Hello. And this string represents the water around the Earth. If we didn't have gravity to worry about, the water would all be equally deep around the Earth. But here comes the moon, this mushroom. Now, the moon has gravity, and that pulls the oceans towards it a little bit, like this. And that creates high tide there, and low tide here, and a little bump of high tide on the other side of the Earth. And as the Earth rotates and I'm on it, I experience low tide and high tide, and low tide and high tide. Very interesting. But there's another factor. The sun, or this lemon. Now, the sun also affects the tides, but not as much as the moon. Now, the sun does not affect the tides as much as the moon because it's much further away, but it still has an effect. If the sun was here, then the tides would be pulled away a little bit like that, and the tides would be less severe. But if the moon and the sun line up, like over here, you'd get a very, very high tide and very, very low tide. So there you are. That's how the tides are affected by the gravity of the moon and the sun. Delicious.
I'm Buster Beaker, and thank you for joining me on Cooking with Science.
Our maxed out hoop glider was working pretty well,
That was
Pretty
amazing.
good. Here we go.
but we could only give it so much thrust by throwing it. So we came up with the perfect Science Max solution.
Our giant slingshot.
We pull the bungee cord back and hook it onto our hoop glider.
I am ready to fire. Count me down.
3, 2, launch it! Very nice!
Our Slingshot is amazing. By giving the glider more thrust, that is, more energy at the beginning so it's going faster when we launch it, the glider soars through the air and flies a long way.
That was great. So there you go. Giant hoop glider. Yeah, Science Max, experiments at large. Nicely done.
Nice.
What more could you ask for?
Well, my turn.
Hey, see you next time.
I'm the marker. Take 8. My goodness.
I play the wobble.
Wobble.
The wobble.
Forgot my line. Forgot my line. Going back down.
Wobble, 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 wobble.
Hello? Hello? Hoop glider central calling. Yes? You were having problems with your hoop glider? Oh, what's wrong with it? Oh, you're using it as a phone? Yes, well, that's your first mistake, yeah. Mm-hmm. Today on Science Max, I forgot to tell you my name. My name is, I'll do it again.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! This episode of Science Max Experiments at Large is all about light and bending light to your will.
Huh? Right?
And challenges me to an ever more tricky game of light manipulation. Plus lasers, periscopes, and what does that have to do with light?
Cut to animation!
Find out on Science Max Experiments at Large.
Greetings, Science Maximites. I'm Phil, and today on Science Max Experiments at Large, we're going to be looking at light. Okay. Stay. That wasn't supposed to happen. I was supposed to press that button, and there was supposed to be all these lasers and special effects, but it didn't. Well, today on Science Max Experiments at Large, we're not going to be doing one experiment. We're going to be doing a number of small experiments because we are going to do a light manipulation challenge. I'm going to get an expert, and she's going to challenge me to a game of light manipulation because I am the master of light. Oh. Well, at least the green lights are working. And okay, forget it. I'm just gonna turn it back to normal. Come on, back to. I'm gonna work on that later. I'm gonna need an expert to help me though. Oh, I know. Anne would be really good at this. It really does look kind of weird in here, doesn't it? Oh well.
You okay?
Hi.
Hi,
Ann.
Phil.
Yeah, I couldn't see what I was doing. Here's your lab coat.
Oh.
Thank you for coming.
Great.
Now, you're from Let's Talk Science, right?
Yes, that's right.
All about science education, just like us. Now, you're going to challenge me to a light manipulation game?
A light manipulation game. I've been working on a series of challenges since last time we talked. Each
Awesome.
a little more difficult than the last.
Well, this is going to be great, because I am the light manipulation master.
Okay, well, we'll see about that.
Okay.
Challenge number 1.
Take a seat.
Oh, that's easy enough.
I have written something on the back side of this ball.
Okay.
And I'm going to challenge you to read it.
Okay, well, I'm ready. I might be able to read it from here. Let's see.
All right.
Okay, I see something's written on it, but I can't read what it says.
What if you squint?
It looks like a couple lines, maybe? I can't quite tell.
Any ideas how to solve this challenge, Phil?
And I have to be in this chair?
Well, you can get out of the chair to set up your solution. But
Okay.
when you read what I've written on the ball, you have to be sitting in the chair.
Well, it's light manipulation, right? So wait a minute, I've got flashlights in case the power goes out, so maybe I can use a flashlight. Haha, okay, ready? Pew! Doesn't seem to make it any easier to read. Yeah, I got nothing.
Do you give up already?
No, of course I don't give up.
I told you these were going to be challenging.
This is nothing. I will figure this out. I don't know yet.
You're going to have to get creative.
I don't know yet, but I will think of something.
Okay.
Okay, I will be back. Here, hold the flashlight. Not looking, not looking. I'm gonna go this way.
I'm going to wait right here.
Okay. Have you ever wondered why you end up upside down when you look at yourself in a spoon? It's because of light reflection. Light is made of photons. Let's say that these tennis balls bouncing off this wall are photons of light. Now, when the surface is flat, like a mirror, the photons, they bounce in and straight back out again. But when the surface is curved, the photons don't go straight out, they get reflected. So now, this photon is going over there, and if we had photons on this side, they would I don't even know where those ones are coming from. Then, okay, so we got photons on this side that are going that way, and photons on that side that are going this way. So the top becomes the bottom, and the bottom becomes the top, and that's why you look upside down when you look at yourself in a spoon. Okay, cut to animation, cut to animation!
A lens works by changing the direction of light, too. Lenses are made out of curved pieces of glass. When the photons of light pass through the glass, the curved surface makes their paths change. What was only this big before becomes this big when you see it. Lenses are used in microscopes to see things that are really small, or in telescopes to see things that are very far away. Both times they are making something small appear large. Anne has challenged me to figure out how to see a small object far away, and using a lens is my solution.
Check it out. It's a giant magnifying lens, and I'm gonna use it to magnify the ball so that I can see it.
Sounds great.
All right.
I set the lens in front of the ball, which Anne has turned so I can't see what's on it. I add a light,
Shine it on the ball so that it's a little bit better illuminated.
and then sit in the chair and ask Anne to move it so it's aligned.
All right, so bring it to your left. Yeah, keep going, keep going. Keep going, right about there. Try bringing it closer to the ball. Okay, wait, that makes it smaller. Bring the lens away from the ball. Ooh, wait. Try a little bit further. Ooh, ho, ho, ho.
You're ready for me to spin the ball around?
Yep.
Okay.
It says 71.
Nicely done.
Easy. Solved.
Wait.
What?
That was just the warm-up.
Oh, yeah?
Yep. You ready for challenge number 2?
Challenge number 2!
I've got another ball
Okay.
with something else written on it.
Wait. Are you coming back?
Nope.
Huh. But I can't even see you from here. Like how am I? Huh.
You're gonna have to manipulate the light.
I have to see around a corner? I have to see around a corner. All right. I'll think of something. So you remember the tennis balls in the wall, right? Right? Okay, so the tennis balls are photons, what light is made out of, and the wall is a mirror. Now, right now, the photons are hitting the mirror and bouncing directly back. But what happens if they come in at an angle? Like this. Aha! Those photons are reflecting off the mirror and going that way, which means if I want to see what's emitting those photons, I can see it from here. The same thing happens when you look in a mirror. Oh, okay, mirror. Whoa. The mirror reflects the photons over here. I can see the tennis ball launcher in the mirror, which means if there was a barrier, between me and the tennis ball launcher, I can still use a mirror and the photons would reflect off the mirror and come straight to me, which is how you can use a mirror to see around a corner. In fact, periscopes work the same way. Let's make a periscope right now. Hey, it's dark in here. Oh, right, because I'm gonna show you my laser. So the light from my laser bounces off this mirror in a straight line. Haha, reflection. We can use the power of reflection to make the light go where we want it to. We're gonna build a periscope.
Submarines use periscopes because it's hard to see when you're underwater. A submarine will extend a periscope up above the water. The image up here gets transmitted down here. So someone looking through the periscope underwater can see what's going on up on the surface.
And here's what you need to build it. 2 cartons of milk, 2 small hand mirrors, scissors or a craft knife, a pencil, and science tape, which is the same as regular tape, except you use it for science. And remember, if I go too fast, you can always find these instructions on our website. Step 1, cut the tops off your milk cartons.
Take your mirror and trace out a rectangle as wide as the mirror, then cut it out. Put some science tape on your mirror and stick it in the carton at an angle. Then put a piece of tape on the inside. Then,
get the other milk carton and do the same thing. Put a mirror on the inside and then stack the milk cartons together. But don't stack them with the holes on the same side. Make sure you stack them with the holes on opposite sides. And here is what's going on inside. You've got your 2 mirrors, and one is angled like that, and the other one is angled like this. Light from what you're looking at comes in, hits that first mirror, goes down to that second mirror, and goes to your eye. You can use it to spy on people from below the table. Or from around corners. So there you go, your very own periscope using light reflection. Did you know that your TV remote can be a flashlight? It's true. If you have the kind of TV remote with a little bulb on the end of it, then when you press the buttons, the bulb lights up. Yeah, I know what you're thinking. You're thinking, Phil, wait a minute, the bulb did not light up, and I've never seen the bulb on my TV remote light up when I press the buttons. Well, that's because your TV remote works on infrared, which is a kind of light you can't see, but you might be able to see it with a camera. If you have a digital camera or a camera on your phone, now you can see, It lights up. And because infrared light works the same way as visible light in that it will bounce off a mirror, here's an experiment you can do at home. Bounce the light off your TV remote off a mirror and turn on and off your television. Check this out. You get a mirror, set it up just right, and then aim the remote at the mirror and it turns off the television. Pretty cool, right? But now, let's max it out. I've got a complex series of mirrors set up here, and I'm gonna bounce the light from the remote all over the room. And here's what that pattern looks like.
The light from the remote hits this mirror, which reflects to this mirror, which reflects to this mirror, and then this mirror, and then this mirror, and then finally to the television.
Isn't that cool? There you go. Maxed out remote light bouncing infrared flashlight. I gotta come up with a better name, but still, it's pretty cool. Oh, right. Turn off the television and leave the room.
I solved Anne's first light challenge, seeing something far away, with a lens.
It says 71!
But now she's moved the ball around a corner, and now I have the solution.
Mirror! A mirror will let me see around the corner.
Clever.
Right? Okay, so all I gotta do is put the mirror in a position sort of like that, I guess, and then I'm gonna sit in the chair. If you could help me adjust that mirror. Keep going that way. Keep going, keep going. Yeah, stop. Nice, okay. Go ahead and flip the ball around and I will read the message. It is too small. I can't, okay, I've solved this problem though. Okay, flip it around. The lens, I need the lens So we'll use a mirror and the lens to... Good. Yeah, okay. I'm gonna sit in the chair. You're in the chair. It is backwards. Oh yeah, a mirror inverts the image, doesn't it? Mm-hmm. That's okay, I can solve this. All I need, whoa! Other mirror is all I need to solve this problem. So if I take this mirror and I put it here, let's see, there it is. It says 42.
Nicely done.
I
Nicely
am
done.
ready for anything. What do you got planned for the hardest challenge?
Are you sure you're ready for this?
Totally.
Challenge number 3.
Challenge number 3 starts now.
What? Wait. No. This is a light challenge. How am I supposed to do a light challenge if it's dark?
You have to get creative.
But it's dark. Well, okay, no problem. I will think of something. I will be back.
Okay.
Okay, careful.
I'll be waiting. Careful.
So you already know about reflection, right? That's when the beam of light, say from my laser, reflects off this mirror and bounces in a straight line. But check this out. If I don't use the mirror and I shine the laser against the underside of the water, it also reflects, just like a mirror. This is called internal reflection. If I have a stream of water and I put my laser beam into the stream, you can see that the laser bounces around inside the stream of water. It's being internally reflected, and the laser isn't going straight anymore. It's following the stream of water down where the water goes. Internal reflection. Now I know what you're thinking. You're thinking, Phil, how does this affect me in my everyday life? Internal reflection. Who cares? Well, I can tell you why you should care in 2 words. Fiber optic wires. 3 words, fiber optic wires. You see, fiber optics carry information all over the planet. The internet, maybe even your television, travels through fiber optic wires. The good thing is, because of internal reflection, you can bend fiber optic wires any which way or around corners, and the beams of light continue to go straight down inside the wires and get out the other end, making it go where you want it to go. Internal reflection, science.
Back to our light challenge. I've seen something small from far away, seen around corners, but now Anne has turned off the lights. But I have a solution.
Ann? Ann?
Careful.
Okay. Sorry, I forgot how dark it was in here. Okay, I figured it out.
Okay.
I have a flashlight.
No.
So all I need to do...
No. Hold on.
What?
There's one more rule I didn't tell you.
What's the rule?
You can't use visible light.
How in the world am I gonna do this if I can't use visible light?
It's a challenge.
Wait a minute. Okay, here, hold my flashlight for a second. I'm gonna make a phone call.
Okay.
I think I know what to do. I'll be back. I'll be
Okay.
back.
Oh, careful. Oh.
Oh, hey, good to see you. Speaking of seeing things, let's talk about the rainbow. All the colors of the spectrum organized in a beautiful pattern. But what are the different colors? I mean, what makes them different? Well, it all has to do with the electromagnetic spectrum. This is visible light. All the colors of the rainbow. And take a look at that little black line that goes up and down there. That's the frequency of the light. Light is a wave. You see the wavelength is a little wider out here on the red side, and it's a little closer together here on the violet side? That's because every color of light has a different length of wave or wavelength. And that is what makes them different when we look at them. But if you think that's all there is to the electromagnetic spectrum, then you're mistaken. So what happens over here on the red side? Does it keep going? Yeah, it does. What?
look, we got infrared here, and then we got microwaves. These are the same kind of waves you use in your oven. And then we got radio waves, which are the same kind of waves you use in your radio. They're all part of the same thing as visible light, huh? Let's take a look at the other end. Remember these short wavelengths over here beside violet? Well, does that keep going? Yeah, if they keep getting shorter, you get ultraviolet, and then X-rays, and then gamma rays, huh? Pretty amazing. And look, it's all connected. From radio waves to gamma rays to visible light in between, it's all frequencies of electromagnetic radiation. How is it staying up? So everything outside of the visible spectrum is invisible, right? Wrong! Ha-ha! Bam! Huh?
That is an X-ray, a picture we can take using this part of the spectrum.
We can use special cameras to see outside of the visible spectrum. Huh? Huh? Right? Yeah. Okay, you got it. Huh? And look at these. These are night vision goggles. They help you see in the dark. They use part of the spectrum called infrared.
For those of you keeping score, that's this part of the spectrum right here.
Pretty neat, right? I would sell you these, but they're already spoken for. Oh, and here he comes now. Hey, Sal. Hey, how you doing?
You got those goggles I ordered?
Yeah, go ahead, help yourself.
Thanks for putting them aside. Can I put them on my tab?
Yeah, no problem.
All right, thanks, Sal.
Okay, see you later. Nice kid. He's always in a rush, though.
Phil? Is that you?
Yeah,
Do you need the flashlight?
I don't. Turn it off. I can totally make my way over to you. Oh.
I can hear you.
Yeah, I'm right here.
Oh.
Right here.
Hi.
Because I have night vision goggles. Ooh, check it out.
Oh, cool.
Pretty cool, right?
That's awesome.
So here's the spectrum again, and here's visible light. My night vision goggles use infrared, this part of the spectrum here with wavelengths just a little bit longer than the red we can see.
Outside of the visible light spectrum.
All right, I would say that's allowed.
No visible light, and I will see the next ball. Have you got it set up?
I set it up while you were out.
Okay, good. I'm gonna sit in the chair and see if I can see it.
Okay, here we go.
Oh wow, I can totally see everything.
Can you tell me what the ball says?
It says you win.
Nicely done.
So let's recap. This challenge is the same as the last challenge. The light from the ball was magnified by the lens, sent around a corner by reflecting it off a mirror, and flipped back around by using another mirror. But this time, it's dark. So, using infrared light, thanks to my night vision goggles, I was able to see the ball and win the game.
The light manipulation challenge is done. Science Max experiments at large. Time to turn the lights back on.
Yep, absolutely.
Huh.
What did you do back there?
I guess we blew a fuse or something.
Uh-oh.
These are night vision goggles. They use some of they use some things that I cannot pronounce.
Have this container of water. What? And I make it stream. But instead of going straight back, they're going.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Today, Science Max is all about sound. We bend the power of sound to our will by making the loudest sound we can.
A subwoofer.
Make cornstarch mud dance, glasses break, and things vibrate. It's the sounds of science. Today on Science Max, experiments at large. Greetings, Science Maximites, and welcome to... Can you hear me? Greetings, Science Max! You can't... Hold on a second.
Greetings, Science... Yeah, that's much better. Greetings, Science Maximites, and welcome to Science Max Experiments at Large. Today, we're going to be talking about sound. Sound is all around us. We use it every day, but what is it really? Sound is energy. Let's say that this is the... No, stay. Stay. Okay. That this spring is the sound of my voice. When I make noise, it travels away from me in a wave. One air molecule vibrates the next air molecule, vibrates the next, and it looks like a wave. And when there's a little bit of energy, the wave doesn't move very much. Science. But when there's a lot of energy, the wave moves a lot. Science! What do we do? What do we do to make sound louder? This is the Science Max theme song. But it's not very loud because the speaker on my phone isn't designed to make super loud noises. So what we're going to do is find ways to make the volume of that song as loud as possible. Here is one way. Take a phone playing some music and put it in a glass. Make sure the glass is empty, of course. Huh? And suddenly, it's a lot louder. Wow! Why this works is one of the things we're gonna be looking at today. So that's what we're gonna do today on Science Max Experiments at Large. We're gonna learn how to make sound louder, as loud as we can. But I'm gonna need an expert to help me. Oh, I know, Michaela from the Ontario Science Centre. She's very smart. All you need to do is go to the Ontario Science Centre and see if she's busy. Yeah, Michaela, it's good to see you.
Nice to see you too.
That was weird. I was wondering if you could give me a hand with an experiment.
Oh, I'd love to, yeah.
It's a sound experiment.
Sounds awesome.
Right on. Okay, we'll take the portal. We'll go back to Science Max headquarters.
Oh, we can take the portal? Cool.
Haven't you taken the portal before?
No, don't you remember? It wasn't working last time.
Oh, well, it's
Is it working?
fixed this time. Yeah, no, it'll be great. Trust me. Here we go.
Whoa. What's going on, Phil? Is everything okay?
Usually when I come through the portal, I land on something or something falls on me or...
Not today. It's your lucky day.
I guess so.
Safe landing.
Safe
Nice.
landing. High five. All right, so let's get started.
Okay, cool. Woo!
This is the experiment I want to max out today, Michaela. I know. Pretty impressive, right? No, hold on.
Okay.
So I take my phone and I play some music on my phone and it's louder, right?
Check it out. Phil, you've just made yourself a resonance chamber.
A resonance chamber.
A
Very
resonance
nice.
chamber is what we say when we're trying to describe how the sound is amplified. So if the sound's coming in from one direction, it's bouncing around, not really losing energy. So when more sound comes in, that's amplified. We hear it a lot louder.
That's cool. So that's what I want to do. Hold on, let me turn this up. That's what I want to do today. I want to max out as much sound as we can get out of the Science Max theme song, which
I'm
is
so excited.
totally awesome. So what else can we do to do that?
Well, there's a couple avenues I'm thinking. Do you want to try something with electricity or without electricity?
That's because with electricity, we're talking speaker systems and
Yeah.
Right. So
We
why
can
don't we
get into
do no electricity for now, and then
All
we
right.
can jump to electricity when we feel we've exhausted everything that's non-electric.
Cool. So I was thinking we could try to make a megaphone because if we have a lot of sound, we could, funnel it in one direction and then it would be louder.
Okay.
What do
Yeah.
you
So
think?
the megaphone's pretty easy to make, right? We could just use. In fact, we could use this piece of paper, right?
Yeah, let's try it. What do you think?
I think it's very megaphony. Science taping it up. Okay, ready? Okay, turn it on. Play it. And doesn't sound, but what if I do this?
Hey, there it is. Right on.
Oh,
That song.
yeah? You hear it?
Yeah. Oh, I hear it.
Okay. So that worked pretty well. So,
Oh, yeah, it works. Works, Phil.
so this is pretty easy, right?
Yeah.
Megaphone?
Oh, yeah.
So why don't we max this out? Why don't we make a giant megaphone and see if it makes a big difference?
I think it will. Let's do it.
Sounds good. Let's get started. vibration, but it's really hard to learn about that vibration if you can't see it. I mean, sound is invisible, right? Well, here's a way that you can make sound visible. All you need is some plastic wrap and salt and a bowl, just a regular bowl, and an elastic, like this. So what you do is you take the plastic wrap and cut off a piece just large enough to fit over the bowl, and then use the elastic to wrap around the bowl to keep the plastic tight. Pour some salt on the bowl, and then watch this.
Hello, vibrating salt.
The plastic wrap is stretched tight over the bowl, making it like a drum. A drum that's very sensitive to sound vibrations. Your ear works the same way. That's why we call it an ear drum. The vibrations from my voice make the plastic wrap vibrate, and that makes the salt dance.
But there's more. Let's max this out. This is a Chladni plate, and what it is just a piece of metal on a platform that vibrates up and down to a frequency which I can program with this dial here. And when the sound waves vibrate the plate, they can interact in ways that make the sand form interesting patterns. Take a look.
The sounds I'm generating vibrate the plate, make it move like a wave. But when the vibrations reach the edge of the plate, they bounce back and interact with the other waves going the other way. The way these waves interact at different notes is what causes the sand to make these different shapes.
So this is great, but you know what? We can max it out even more. Maxing it out even more. Okay, that's about as much as I can take of that. Whoa.
So Michaela and I are on a quest to make the loudest sound we can. The first step is to make things louder without using electricity. We've looked at a resonance chamber, and now we're going to make a large megaphone. Sounds can be amplified by bouncing sound waves around in a space. When I put my phone into the glass acts as a resonance chamber. The sound waves bounce around inside the glass, and they combine and stack on top of each other. This makes the sound louder. Resonance chambers are used by musical instruments like an acoustic guitar. The wooden chamber bounces the sound waves around, and the sound waves build on each other to make the sound louder. A megaphone bounces sound waves as well. Instead of going off in all directions, a megaphone makes the sound waves all go in one direction. That's one of the reasons why a megaphone makes sounds louder, but only when it's pointed at you. So will a bigger megaphone work better?
So we've made a larger megaphone, which is exactly the same thing. You just take a sheet and you roll it up, except our sheet was plexiglass covered in paper, and we've taped it together so it stays. And the idea here...
Oh yeah, bigger megaphone. We're gonna vibrate even more of the air inside of here, and hopefully this thing will be louder.
Okay, so you're ready to try it with the phone?
Yeah.
I think first we should try it with our voices, though.
Okay.
Now, what's your favorite season?
Awesome, I can totally hear you. That's amazing. And it would be fall. No, summer. Spring?
Think
it's
about it.
anything but winter.
So the maxed out megaphone worked, but we still had to try it with my phone.
Okay.
All right.
Yeah?
Oh yeah. Oh, definitely.
How about now?
No, not so much. Not so much. Oh yeah. Nope. Nope.
So that is a
That was
great
cool.
example of non-electrical amplification.
That's right.
Amplified the sounds, no electricity. Okay, high five. All right.
Come on, make some noise! Well, how do you make noise? Well, to know that, you gotta know your sound. All sound is vibration. Here, take a closer look. You see? You got... Okay, let's try this again. All sound is vibration. The string of this guitar vibrates, which vibrates the air around it, causing the sound that you hear. Your vocal cords vibrate in your throat, causing you to make a sound. Ah, 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 la, 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 la. Look at this thing. Look at this thing. See how it's shaking back and forth? It's vibrating. Things that make a high sound, they vibrate faster. Vibrating really fast. Things that make a low sound vibrate slowly. High note, vibrating fast. Fast! Fast vibrating! And now you know your sound.
Everything has a resonance, a note that it vibrates best at. Let's say this fish tank is, well, any container where sound would be vibrating, and the waves of water are actually waves of sound. Now, normally, sound waves will bounce around inside the container, off the walls, and go back and forth like that. And how fast I move this piece of wood is the frequency, or the note, that we're playing. I could vibrate this wood very fast and make a high note. I could move this plank very slow and make a low note. And the waves just bounce around inside the container. But there's a speed I can move this plank where the waves stop going side to side and suddenly get twice as big.
The waves bouncing off the sides of the tank are meeting the waves going in the other direction. But what we end up seeing is peaks of the waves not moving side to side, just going up and down, like you see here.
This is the resonant frequency of this container. So, let's max this out. Say I have a wine glass, and I wet my finger, and I rub it around the rim. It vibrates at a certain note. That note is the resonant frequency of this wine glass. So what would happen if we were to play that note back to this wine glass really, really loud?
And yes, this is something you should not try at home.
This note makes the glass vibrate the most.
Finding the perfect note things vibrate best at is great for musical instruments, but it's not great for this wine glass. The sound waves are causing the glass to vibrate a lot. And because this glass is delicate, it can only vibrate so much before it breaks.
The vibrations were so strong that the glass literally shook itself to pieces. Science! Sorry. Science! Oh, wait. Science!
Michaela and I have tried a resonance chamber and a giant megaphone to make sound louder. Now it's time to move on to the next step of the plan, using electricity to help us amplify sound. And that means speakers!
So, speakers that you have at home, 3 different speakers here, right?
Looks
3 different
really busy.
cones.
Yeah, there's a lot going on.
So, what's the deal?
Well, here at the bottom, we have a subwoofer.
Wait a minute, a subwoofer.
Subwoofer.
So it's a woofer, the word is woofer?
Yep.
And it's, okay, so it's for dogs. Right?
No, a subwoofer is for low notes here in our speaker.
Ah.
At the top here, we have a tweeter.
So it's for birds. It's it birds, dogs. So low, let me guess, low notes?
Yeah.
Tweeters, high notes?
Yeah, high notes. And then we have this guy here in the middle, and that's called your mid-range speaker.
Oh, that's not nearly a cool name. Now we have speakers, we've taken a look at that, but why don't we take one apart,
Cool.
right?
Yeah, let's do it.
I've got this one here that I spilled juice on, so it doesn't work anymore. So I've kind of taken it apart. So
Cool.
it's got,
Man, that's awesome.
okay, so it's got the cover. That's cool. So what I find interesting is there's the speaker and the wires, right? Because it's electrical amplification. But check this out. This is just a ring to hold that on. And the rest is just an empty box.
We know what that is. Resonance chamber.
That's right. So that's why it's an empty box. So
Let's take this apart too, see what's going on.
So that's the paper cone, right? So that's the drum, I guess. It's like the eardrum, the thing that vibrates.
Yes, yeah, this little thing vibrates.
So that this whole thing.
That's for electromagnet. When we turn this on, the electromagnet goes on and off, and it's causing this whole thing to vibrate.
So that's how it works. It's the electricity turning the electromagnet on and off.
Exactly.
And it's on and off and on and off and on and off and on and off. And then it makes it vibrate at certain speeds, right? Hertz. The number of times it vibrates per second is hertz. What we could do is we could max it out with the speaker and plug the phone into the speaker. But this step does not feel like Science Max to me because anybody can do that, right?
Yeah.
You can just turn up your television right now, and that's pretty much the same kind of thing. We need electrical amplification, but maxed out.
Max it up. What are you thinking?
Okay, so I've got a friend, and he's got a stereo system that he built, he put together, and what he does is he tours different cities. So he said he'd bring it by Science Max headquarters.
He's gonna bring it here?
We gotta go outside.
We can see this thing.
And it's very loud, so we have to go outside.
When's he coming?
Right now. All right, let's go check it out.
Seeing sound vibrations is fun.
This kind of speaker is a special kind. It's called a subwoofer, which is designed to give you the low notes, the big rumbly bass sounds.
I tilt the speaker so it's facing up and cover it with big sheets of plastic wrap, which I push into the cone. Then, tape it so it's nice and secure.
Then, what you need is some cornstarch mud, which is 2 parts cornstarch, 1 part water.
I've got some yellow cornstarch and some blue cornstarch.
This experiment works the best with low notes.
I'm playing a tone through the stereo that is very low. Here's what happens when I turn up the volume.
It's alive! You see, cornstarch mud is a shear thickening fluid, which means when you impact it, it turns solid. So the vibrations from the speaker cone are making the cornstarch mud impact, and that's turning it into a solid. But then it sort of also melts back into a liquid, so you get little columns of cornstarch coming up and falling down again. It's like it's dancing. Whoa! Visual sound waves. Science!
So Michaela and I are going to max out sound. To do that, we need a maxed out sound system. Isn't it amazing? This is gonna be super maxed out sound experiment. This is James, Michaela.
Hey, James, how are you?
Thanks for coming, buddy.
Nice to meet you.
So, tell us about your speaker system. It looks a lot like a vehicle.
This is my audio van. It's got 4 15-inch subwoofers in the back. It's got a whole bunch of power to power it, and I'm glad to be here to let you guys hear it today.
Wow.
So if I have a speaker at home, like a little speaker like this, how many watts do you think that would be?
Somewhere between 15 and 25.
15 and 25 watts.
Yes.
And you've got 4,000.
Yes.
So that's a lot more.
Yeah, quite a bit.
And subwoofers, they play low notes.
Yes.
So is that better when you have a van like this?
With a car audio van like this, you want to play low notes, like your house stereos, and that will play anything from 120 to 200 hertz. I'm playing 20 hertz to about 35 max for you guys today.
So that's like a sort of rumble of thunder,
very
kind
low.
of blah, 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 where you really feel it, like a train going past almost.
Oh, that's cool.
So we get our hearing protection on and we try it out. I know what you're thinking. Phil, what's the point of having loud music if you can't really hear it? Because we've gone from listening to music to feeling it. The sound waves are so strong that they have become a physical presence. Michaela's hair flies around because the air from the speakers is creating shock waves. The sound waves are so powerful, they move the air back and forth, which makes Michaela's hair dance all over the place. And my hair, not so much.
jealous of your long hair?
Yeah, you need to get longer hair.
Okay, hold on. I'll go right.
Okay.
Whoa! Science Mac, experiments at large, super sound! High fives. Okay, ready to go again?
So cool. Yeah, let's do it.
Okay, here we go.
At the bottom.
I can't reach it. So that's great. Wait, almost. No, I can't. Okay, I got my hair protection on.
Right on.
You got your hair protection on?
What's that?
Hello? Oh, hi, Mom. No, I'm shooting the show right now. I can't. Science.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! It's time to get stuck on magnets. What's our attraction to magnets? What's their attraction to each other? And can I use magnets to levitate and float in the air? All on this episode of Science Max, experiments at large.
Greetings, Science Maximites. Welcome to Science Max, experiments at large. My name is Phil, and today we're going to be looking at the power of magnets. You see, magnets are fun things to experiment with because they are really, they're really interesting. This magnet that I've got here is a neodymium magnet, or a rare earth magnet. It's one of the strongest magnets you can get. A magnet is an object that is attracted to anything that is ferromagnetic, which is iron, nickel, or cobalt. And magnets are interesting because they have two sides. There are two poles. I'd show you, but I can't get the chain off. Hold on one second. Ha-ha! There are two... Oh, no. There are two poles to every magnet, just like the Earth. There is a North Pole and a South Pole. That's right, the Earth is a giant magnet. So, if you take kitchen magnets, you'll find that there's two different poles. I've written north and south on these ones. They don't normally come like that. If you put the north and the south together, they stick. But if you put the north and north or south and south together, they repel. They repel, see? They don't want to go together at all. And you can force them together if you want, but if you do, they will spring away the second you let them go. Whee! But when magnets repel each other, I find that some of the most interesting stuff. Check this out. This is just a small container, and I've got a magnet in here, and I have a loonie attached to it so that it fits nicely in the container like that. For the top, I've attached two magnets together, and I have another coin on it. And if you put them in there, I've made sure that the two poles repel each other, which means this magnet will just sit there and float. Magnetic levitation. Very interesting. And you can pop the top on that if you want and just carry around a levitating magnet. Now, there's a couple fancier ways you can levitate stuff with magnets. This is just a wooden frame I've made. This is completely not necessary. You can use just about anything in your house. A desk lamp works really well. The important part is I've tied a magnet to the end of this arm here, and this is a bolt, which is attracted to the magnet, but it's got a thread tied to it, so it can't get there. Just far enough that it will actually hang in mid-air. Look at that. It's not attached to anything. It's just being pulled up by the attraction from the magnet. The thing is, as soon as you pull the bolt away far enough, it will lose the attraction and it'll just fall.
Very cool. Here's one that's a little bit more complicated, but is also really neat. This one uses disc magnets, which have a circle or a hole in the middle of them here. And you put 2 around a pencil and then 4 more in such a position that you can put the pencil against this wood on the side and it will just levitate on its own. You can even give it a spin. Look at that.
And if you want to make the levitating pencil yourself, there's step-by-step instructions on how to build an easy-peasy version on our website.
Meantime, we are gonna max this out. Magnetic levitation on Science Max Experiments at Large. But you're probably thinking, what are we going to levitate? Well, we're going to levitate me. At least, that's the plan. That's why I'm going to the Center for Skills Development and Training. Come on.
Okay, who turned out the lights? Ow, what was that? Why is this room so small? And only going down to waist level. This is the weirdest room I've ever been in. Where am I? What's going on?
Hey, Matt.
Hi, Phil.
This is Matt. He's from Jobmaster Magnets. Now, you guys use lots of big magnets, right?
That's right, we do.
Awesome. So maybe you could help me max out this.
Wow. You did a great job of building the levitating pencil experiment.
Yeah, so what's going on here exactly?
Well, all magnets have at least a north and a south pole.
Right.
And when you put like poles together, they want to repel.
Oh, okay. So have you ever levitated a person?
Not yet.
Well, let's do it.
All right.
Do you think we can use these?
We can try.
Okay, well, put that one on the ground. And, okay, so north, and I'll put the north one on my foot here. And then if I just step, oh, wait a minute. If I step, stop moving. If I step on the, okay, well, first of all, this magnet keeps sort of moving away from me when I try to push down on it. What do we do? How do we fix this?
Well, we need to keep the magnets in position so that they don't move around when you try to bring them together.
Yeah, because I have to come straight down on it, don't I?
That's right.
So why don't we attach this one to the floor?
Good idea.
And then we'll put a board on this one, and we'll see how it goes.
Perfect.
Okay, let's do it.
All right.
This is a magnet. This is a magnet. This is a magnet. This is a shoe. What's the difference? To know that, you have to know your magnets. This is a donut. It does not stick to this magnet. This is a spoon. It sticks to this magnet. These paper clips stick to this magnet. This shoe does not. So what is attracted to magnets? Only things that are ferromagnetic. Here's the difference. Horseshoe, horseshoe magnet. This one is a magnet. This one is not. But the horseshoe sticks to the horseshoe magnet because this one's a magnet and this one is ferromagnetic. Only things that are ferromagnetic are attracted to magnets. Things that are not attracted to magnets, they're not ferromagnetic. Plastic, banana, mitten, sandwich, magazine. No, but how do you know? Do you go around the world sticking a magnet to every single thing one at a time? Hey, Ma, I need you to come over. I need to see if you're ferromagnetic. No, ferromagnetic. No, you don't need to do that. First of all, only metals are ferromagnetic. So that eliminates all your clothing, your luncheon meats, your magazines, what have you. Everything that's non-metal, you don't need to worry about. Never mind, Ma, it doesn't matter. But this clock is metal. It doesn't stick. Well, not all metals are ferromagnetic. Mainly just the ones with iron, nickel, or cobalt. And there you have it. Now you know your magnets. I hit the phone on the magnet there. Okay, can you hear me, Ma? Hang up the phone. Hang up the phone, Ma.
My first attempt at levitating had the magnet sliding all over. So the plan is to take the bottom magnet and attach it to a big wooden board so it won't go anywhere. Then attach another plank to the top magnet to make it a little easier to stand on.
Okay, that is definitely attached to the floor. Thank you. All right, now, if I just get this lined up. Whoa, look at that. It could totally, oh, wait a minute. Totally, it doesn't want to stay put. Oh, wait a minute. They levitate. Come on, levitate. Why doesn't it want to stay? It just doesn't. Should I stand on it? Okay, I'll stand on it. Here we go. And, am I levitating?
No.
No. So why isn't this working?
Well, just like your pencil experiment, we need a shaft through the center to hold the magnets in position.
Oh, yeah, maybe we could use like a ring magnet.
Yes.
That like we used with the pencil.
Right.
And
we're gonna need stronger magnets.
we're gonna need stronger magnets. Are the ring magnets strong?
Yes, they can be.
Awesome. All right, let's do it.
All right.
Now it's time for a Science Max quiz. Which one of these things do we have magnetism to thank for? Birds flying south in the winter, music, or a sandwich? If you picked A, you're right. Some birds migrate in the spring and fall using the Earth's magnetic field. Many animals can sense the Earth's magnetic field and use it to navigate. Migrating birds fly hundreds or thousands of kilometers north or south when they migrate in the spring and fall. A compass works the same way, by using magnetism to point to the Earth's magnetic North Pole. But if you picked B, music, you're right! Here's some music. The way you're hearing this music is because the musicians recorded their instruments using microphones, which use magnets. And then the signal was translated by a computer and stored on its hard drive, which uses magnets. Then it was broadcast to your TV and comes out your speakers, which use, you guessed it, magnets. And for those of you who said you have magnetism to thank for your sandwich, well, you're right. You see, you'd probably go to the kitchen to make that sandwich, right? Well, I'm guessing you got all of the tasty ingredients from your refrigerator? Well, it works on electricity, which is produced by magnets. And then there's an electric motor in the fridge that circulates the air and keeps it cool. And guess what? Magnets. And finally, the door on your fridge stays closed because the door has magnets. So there you go. You can thank magnetism for birds flying south, music, and your sandwich. It just goes to show, when you're talking about magnets, everybody wins because magnets are everywhere. This has been a Science Max quiz.
Mini Max.
Here's an experiment you can do with a bag of water. Take a sharpened pencil and carefully push it through the bag. If you do it carefully, it won't spill. The reason this works is because the bag is made of polymers, long stretchy chains of molecules, and also because the pressure of the water against the pencil prevents any water from spilling out. Now, we're gonna max it out. This is a very large bag of water, and here I have some very large pencils. You ready? Oh. That's one. That's two. Here we go. Should I go from the bottom? Ta-da! Science! Okay. I know what you want. Like I was saying, science! Turns out, trying to balance two repelling magnets on top of each other is pretty much impossible. Here's why. This is a magnet, and here is the magnetic field. It's often drawn with lines like this, but actually the magnetic field radiates out in all directions. Really, think of the magnetic field kind of like a ball. When you try to balance another magnet on top of the first magnet, it's about as hard as balancing one ball on top of another ball. So here's the plan. Just like the levitating pencil, we're going to use ring magnets because we can put a shaft through the center of one ring, then drop another ring magnet on the shaft. It will keep them perfectly aligned. Then it's just a matter of putting the bottom magnet on a board to keep it stable and using another board so I can stand on it, and ta-da! Magnetic levitation! Or at least that's the plan.
Okay. Board.
Magnets.
Magnets. Ooh, look at that. Awesome. And now I'm gonna put the platform on. Nice. I got some weights here. Let's see how this works. Yeah. This is gonna work amazing. All right, think I should try it?
Give it a try.
Okay. Here we go. Yeah! I'm doing it! I'm levitating! What?
Just a little bit.
Oh, really?
Yeah.
So, yeah, what do we do?
We need more power.
More power? I like that idea. How do we give it more power?
More shafts, more magnets.
Okay, sure. Well, why don't we do 1, 2, 3, 4 shafts, and then we'll have magnets on all the shafts.
Great idea.
All right. Let's do it. If you attach something ferromagnetic like this washer to a magnet, not only does it stick, but the magnetic field travels down the metal, making it a magnet too, which means you can stick more and more things to each other, and they will continue to stick until you run out of magnetic field. You can do this yourself at home with anything ferromagnetic. Paper clips work pretty well, or washers like I have, or screws or bolts, and they'll continue to stick to each other as long as the magnetic field is strong enough. You can see it's getting pretty weak here, and they'll all stay magnetized as long as the first one is still attached to the magnet. But if you want to go even further, all you need to do is keep adding more magnets to reinforce the magnetic field. I've got a few here, like this. Let's get the chain started, like that. And then I've got a magnet attached to this washer, so it will keep the magnetic field strong. And I continue to add one magnet, one washer, and we'll just see how far I can go. You can even sculpt it a little bit. Look at that. And then at the end, a whole bunch of paper clips. Eventually, the weight will make it fall off, but it's a lot of fun to play with magnets and make art. Speaking of art you can make with magnets, you can also make sculptures. When everything sticks to everything else, you can make some pretty fancy designs. This is a rare earth magnet, a very strong one, and a bunch of nuts that I've gotten. And this one here is an electromagnet, but electromagnets are a little different because they need an electric current to work. Check this out. This is sort of a magnet dude with crazy hair. There's an earth magnet here, and this is a giant screw, and these are some metal bits, and then I've got 2 more magnets at the top here to hold on his crazy wire hair. He's got crazy wire hair because he's crazy magnet dude. Now, of course, we couldn't just talk about magnetic sculptures without maxing it out, so let's max it out. This is a bunch of scrap metal from leftover experiments, and I've got a bunch of rare earth magnets, and now I'm gonna max out a magnet sculpture. Let's see. There you go, a maxed out magnet me. I made this guy out of metal pipes with earth magnets in between, and these are his arms attached, of course, with magnets. His hand, his little metal pieces attached with magnet. Steel wool for the hair, and of course, hat, non-magnetic. All right, here we go, ready? Want to see a magic trick? Simple copper tube. Drop things through it. Nothing unusual happens, but watch when I drop a magnet through. What? It's not magic, it's science. Because the magnet creates a magnetic field, when it goes through the tube, the magnetic field repels the magnet upwards. Now, the field isn't perfect, so the magnet doesn't come to a stop, but still, it slows down from a fall to a nice, graceful drop. Take a look from above. Pretty amazing, right? Magnets, not magic, science.
So I've managed to levitate on some magnets, but just barely. What Matt and I needed was more power. So instead of having one shaft and one pair of ring magnets, we're going to use a larger board and put a shaft on each corner. Then we'll have 4 times the power because we're using 4 times the magnets. Hopefully this will be strong enough to get me floating on a cushion of magnetic energy.
And magnets?
Magnets.
Okay, here we go. This is gonna work great. And top board. Ooh, what do you think?
Looks great.
Yeah. Okay, here we go. Matt?
You're levitating.
I'm levitating! Woohoo! All right. It feels cool. It sort of feels like surfing a little bit. All right, thank you so much, Matt. That was amazing. And there you have it. Science Max, experiments at large, magnetic levitation. You know, I'm surprised we could do an entire episode on magnets, and we never actually got them so close to the camera that the camera went all weird, because cameras and magnets, they don't, oh dear. No, that's okay. I can fix this. If I just maybe, maybe if I put the magnet to the camera again, that would, okay, that's not, that didn't help. Oh, okay, well, thanks very much for watching Science Max, experiments at large, and we'll see you again as soon as we get into the camera. Today, we're gonna be looking at the power of magnets. 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 Wait, okay. This one here is called a neodymium magnet, or a rare earth magnet.
It sticks to this magnet!
Ramona, the fish fell.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max!
Try yours. Here you go.
What makes airplanes, or basketballs, or people fly? It's air. As well as a bunch of other things that we learn when we try to make a giant paper airplane.
So that didn't work.
All on this episode of Science Max, experiments at large.
Greetings, Science Maximites. Today, we're going to be looking at air. I know, it's kind of hard to look at air because it's invisible. But we can look at something that uses air to move. That's right, paper airplanes! Ha-ha! Ha-ha! Look out! Woohoo! Believe it or not, you can learn all kinds of science from paper airplanes. So let's build some. We are going to do a paper airplane which actually holds the Guinness World Record for the longest paper airplane flight. Pretty cool, huh? First, you fold the paper in half like this, but then you open it back up again, and then you fold in the corners like this. Now, don't worry if this is really, really fast, because you have all the instructions on our website. Then you can fold the paper down like this. Make sure it's about 2 centimeters from the bottom, where the point is there. And then you fold the corners in just like you did before. But these ones are just guide folds. We use guide folds to help us fold other folds, basically. Now, we fold again using the guide fold lines you just made. And I like to call this fold the shirt collar fold because it sort of looks like a shirt collar when you fold it. Now, we fold again on the fold that you made before. Folds in like that and in like that. And now we fold the point down to touch the edges right like that. And this is a guide fold, so do it very strong. Unfold it. Now you fold it in half like this. And see that guide fold line that we made there? What you're gonna do is you're gonna take the tip and you're gonna fold it in to touch the guide fold line like that. And this is also a guide. And open it up. And here's the trickiest part. See how it's bent like that? You push it open like this. And this is called a pocket fold because you wanna make a little pocket and push it up against there. Fold it flat like this. Fold this tip down over there like that. Then fold it around the back side. Then fold the wings down like this and like this. And here's the extra special bit. We're gonna use some stabilizers on this plane. Fold up the stabilizers on the ends of the wings and ta-da, the Sky King paper airplane fold. Now, as science maximites, you know that there's lots of ways you can learn how to fold paper airplanes. Get an adult and look up paper airplane designs on the internet, or take a book out of the library on how to fold paper airplanes. And of course, this isn't Science Max, experiments at large, if we don't max it out. So that's right, we're gonna make a giant paper airplane. I'm going to the Ontario Science Centre to do just that. Uh-oh, that's never good.
Whoa, Phil, I'm so sorry. You okay?
Yeah, I'm okay, Justin. I never know where the portal's gonna spit me out. This is the Science Center, right?
Well, that's right. In fact, you've landed in our paper airplane laboratory.
This is what happens to me, Justin. I make a paper airplane, I fold it perfectly, but then it flies like that, or it does that, and I don't know how to fix it.
Okay, well, that will happen. But you know what? There are really only 3 ways your paper airplane can fly, and I can teach you how to control each and every one of them.
Great, let's do it.
Let's do it.
All right.
Science Max presents How to Fly Your Paper Airplane. Is your paper airplane spinning around and around? Well, that's what you call roll, chum. Roll is what you call it when any plane moves like this or like this. Here's how to fix it. Bend up the back of one wing to create more lift on one side, and it'll balance out. Happy days.
Okay, so let me try mine.
What's that? Your airplane goes straight up or straight down? Sounds like you have a problem with pitch. Sorry, pitch. Pitch is when your airplane moves like this or like this. To fix it, bend the ends of both wings up if you pitch down, or down if you pitch up. Adding a weight to the nose also helps if you've got a problem with high pitch. High pitch.
Great, great, your turn.
All right, here we go.
Is your plane turning this way or that way? Yeah. Yeah? No. Yeah. Yeah is when your plane moves like this or like this. To fix it, bend the back of the plane like the rudder of a boat.
Okay, great. Let me try mine. Not bad. You try yours.
Here we go.
Oh, yeah.
That was pretty cool.
That's what we want.
Yeah.
You know what? Are you ready to build a giant paper airplane?
I think I am.
Fantastic. I just need to get one more expert. I will be right back.
Cool.
Hey, David, how you doing?
Hey, good.
Good. So David's going for his Masters of Applied Science.
In aerospace science and engineering.
So you know all about planes.
I do.
Great.
Yeah.
So what does this have to do with planes? What is this?
So this is a water channel, and it allows us to test airplanes in it before we put them in the sky.
Great. We'll have my airplane, and we'll just put it in here, and we'll test it.
Please, it's made of paper.
Yeah?
And in the water, it becomes soggy.
Well, how do we test our paper airplane if we can't put it in the water?
Well, this is a classic airfoil shape.
Yes. Now, is that what you call it, airfoil?
An airfoil, yeah. So the cross-sectional shape of a wing is called an airfoil.
Okay.
And that's what generates the lift. Fortunately, air and water are both fluids, so they behave in the same way. I could push ink into the water, and that's going to allow us to see how the fluid flows over the aircraft. So if you tilt its nose up a little bit, you'll be able to see that the shape of the airfoil is actually pushing the water downwards.
Oh yeah, you're right. The ink doesn't go straight. It follows the wing down.
It follows the shape of the wing down, and we have a lower pressure on the top of the wing and a higher pressure on the bottom of the wing, which pushes it upwards.
Right,
generating
and
lift.
that creates lift.
Exactly.
So you guys use this all the time in aerospace?
Yeah, yeah.
That's pretty
Absolutely.
neat. So, are you ready to design an even bigger plane, a giant paper plane?
I'm confident we can do a good job.
I am excited about it. Let's do it right now. The big paper's over this way. This way. Okay.
Here's the plan. Take a giant piece of paper and fold the exact same airplane we did in the lab. The small one flew. The large one should too, right? Well, let's find out.
I believe we are ready to make our giant paper airplane. All we need is a giant piece of paper! Yeah! Okay, be very careful getting off it. Whoa! All right, let's fold it. Nose on that side. Okay.
Remember, we're folding the exact fold we did in the lab, only on a larger scale.
We have a tape malfunction down here.
But it's a lot harder to do with a giant piece of paper.
Fantastic. That's pretty good.
Okay. There.
Perfect.
Yeah. Giant paper airplane! Ha ha!
This doesn't look too much like an airplane.
No, it's way too floppy.
Yeah, but I mean, maybe it just needs, like, when I throw it, maybe it'll catch the winds, and then the wings will come up like that.
Whoa. Yep. Maybe.
Like, I'll just...
Give it a try, Phil.
Okay, I'm gonna give it a try. Giving it a try. Okay, you guys ready?
Yeah.
Go for it.
Okay, here we go. Wow. What do you think?
Oh man.
I think we can make some improvements.
It sort of felt like a bed sheet. I feel if I just threw my lab coat, it'd probably look. Let me just see. Okay, ready? Yeah, it looks pretty much the same, doesn't it?
Yeah.
So, I didn't know this, but when you fold paper that big, it sort of behaves like fabric.
Yeah, very floppy.
Very floppy. What if we supported the plane, like we put struts or something in it, like this stick? If we put it on the wings, it'll stop it from being so floppy.
Right, and you can tape it on.
Yeah.
That's a great idea.
Yeah.
We need bigger sticks.
Yeah.
Really lightweight.
Like
Like
foam.
Yeah,
Stuff?
and like hollow tubes.
Hollow tubes. Good.
Over.
Good. So we'll put a whole bunch on there. We'll tape them on so that it doesn't flop around.
Yeah.
We'll try it again.
Yeah.
Yeah. Take
Yeah.
Okay, great. Let's go.
All right.
Bernoulli's theorem states that faster moving air has lower pressure than slower moving air. You can demonstrate this yourself with a ping pong ball and a hairdryer. You put the ping pong ball on the stream of air from the hairdryer, and because it's moving quickly, it has lower pressure than the air around it. So the low pressure air works sort of like a force field, and you can defy gravity with your floating ping pong ball. Awesome! But of course, this is Science Max Experiments at Large, so we have to max it out with a giant hairdryer and a giant ping pong ball. Sorry, I said science! You probably couldn't hear me because of the...
So, our giant paper airplane turned out to be really floppy. When paper is that large, it doesn't hold together very well. What we're going to do is take foam and long sticks and tape it to the large paper airplane wherever we need to give it support. So, here, and here, here, and a bunch there, and maybe some over there. Well, it turned out we needed to reinforce in a lot of places.
Put that in there, and then that. Great, look at that. It's not even flopping around. It stands under its own weight. Huh?
There's a whole bunch of stuff on it. I don't know if it's gonna fly so well.
Oh, it's gonna be. Well, I mean, I have to put the stuff on it so it doesn't flop around.
But there's like really a lot of stuff.
Well, I needed this foam to reinforce this foam, and then I needed the cardboard to reinforce both of those.
Phil, there's a giant hole in the wing.
Well, I can fix that. Just move your head, and then I'll just.
Phil, there's a lot of stuff on here.
There.
But like, it's really a lot.
Problem solved.
Guys, let's just fly it.
Oh, okay, sure, yeah, let's do it. Let's do it. All right.
Okay. All right, here we go.
Maiden voyage of the Mark II giant paper airplane. Okay, here we go. 1, 2, 3. So it went about 3 feet. So that didn't work.
I told you, too much stuff.
You did. He told me that.
He said that.
He said that.
What we need is something that's stiffer without as much stuff on it.
But the paper, it's too floppy, so you have to put the stuff on.
Right.
How about some cardboard? Cardboard's nice and stiff, and technically it's paper.
You're right, cardboard. Let's make it out of cardboard.
Yeah.
Cardboard, all right. Oh, yeah, it's over here. Tornadoes are giant weather systems that cause the air to go around and around. Tornadoes can be pretty dangerous, but they don't happen that often. Here's how you can make your own small pet tornado you can play with at home. Because air and water behave similarly, we can make a water tornado. You spin it around, get it going, and ta-da, your very own pet tornado. Here's how you do it. You take two 2-liter plastic bottles and fill one with water and some blue food coloring, is what I like to do. And then tape the mouths of the bottles together. You might need an adult to help you with this because you want to make sure the bottles are perfectly aligned. Then flip it over, spin it around to get it going, and voila, your very own pet tornado. Awesome. And now we're gonna max it out with a giant tornado chamber. Hey, Michaela.
Hey, Phil.
So this is your giant tornado. It's amazing.
Yeah.
So I made one with plastic bottles and water, but this one uses air, just like real tornadoes do in the wild.
That's right.
So how does this work?
Well, here we have a platform, but underneath that there's a fog machine that's pushing the fog up. And we've created an updraft because there's a fan at the top that's pushing air out of the top. And also we're trying to mimic the intense winds you'd get from a tornado with these pillars that are shooting out air in this direction.
So it goes around in a circle.
Yeah, in real life, tornadoes are pretty rare. You need a perfect set of conditions to see them. You need warm, humid air and cold, dry air. And as well, some intense winds that you usually get from thunderstorms.
Science! If I was to drop this light basketball and this heavy workout ball at the same time, which do you think will hit the ground first? Let's find out. They landed at the same time. That's because everything falls at the same rate. It doesn't matter how heavy or how light something is. Until things are falling fast enough that air friction or drag starts to play a factor. Soon, things reach their top speed. This top speed is called terminal velocity. It means I could throw this basketball from an airplane and it might not be going any faster than if I threw it from, say, 10 stories up. I'm gonna find out what the terminal velocity is for both of these objects when we max this out. Ninja science roll! Here's how terminal velocity works. Everything falls at the same rate, going faster as gravity pulls it down. But when things start going so fast that just pushing through the air at that speed creates as much force as the pull of gravity, things reach a top speed and they won't go any faster. How heavy something is and how much air it pushes both play a factor in its top speed. And that top speed is called terminal velocity. How cool is that? I'm at iFly Toronto. This is a giant wind tunnel, and they've got the wind going fast enough that they can't fall any faster. It's the terminal velocity for a human being. I'm gonna take our weighted ball and our basketball and place them both here in the wind chamber. This is the control panel, which is what they use to control the wind speed inside the chamber. And this is Derek, who's gonna be operating it. And that is Mike and Greg, and they're inside the chamber. All right, let's fire it up.
All right, firing it up.
35, 58, nothing happening yet. This number here is the one we're looking at to see how fast the air is moving. 86, something's starting to happen. Oh, 89, wind speed of basketball, 89 kilometers an hour. At 89 kilometers per hour, the wind is going fast enough that the friction of the wind and the pull of gravity balance out, making the basketball float. This means you could throw a basketball out of an airplane and it would never go any faster than 89 kilometers per hour.
All right, let's keep increasing the speed. 106, 124 kilometers an hour, 140, 150. Oh, 166, almost. 172, whoa. Wind speed of the heavy red ball, 173 kilometers an hour.
Because the red ball is heavier than the basketball, we need a lot more wind speed to counteract the force of gravity before they cancel out and the ball floats. Here's something else that's going on that's cool. Mike is flying, but Greg is not. That's because Mike is lying down, which means he's catching a lot more wind than Greg is, who's standing straight. If Mike stays lying down, his terminal velocity is the same as the red ball, 173 kilometers per hour. But Greg's velocity would have to be a lot faster. And that's science! So the giant paper airplane hasn't been working so well. The problem is paper can't hold up its own weight when it's that large. Cardboard is much stronger than paper, so we've decided to rebuild the plane out of cardboard.
All right, Phil, hoist it up.
Then we take it to the roof of the Science Center and see if we can get it to fly. Oh, woo! There you go, our Mark III model paper airplane. Now, I know it's made out of cardboard, but cardboard is technically paper, and it's the only thing strong enough to hold a plane of this size together. We even had to put some poles in so the wings still wouldn't flap, but we're pretty confident this is gonna work. Okay.
All right, Phil, we're in position.
Now, don't try this at home. Our roof has a big wall on the edge. Your roof does not. Our first attempt didn't go so well. Looks like we have a bit too much pitch. Our second attempt still had a bit too much pitch. Time to add some weight to the nose. We added some clips to the front to give it a little bit more weight on the nose, which is important. Although at this point, I kind of wish there was less weight. Okay, all right.
Phil, that was great!
Woo! All right! Woo! This throw worked best, but I know what you're thinking. Why didn't it sail through the air like a normal paper airplane does? Well, that's because the other thing heavy planes need to fly is thrust. So we could put an engine on our plane, but then we'd have to use something stronger than cardboard, and well, pretty soon we'd have an actual plane. But this isn't about making a full-size plane. This is largest paper airplane I've ever thrown! Woo! Right! You guys are great! The plane is great! Thank you very much for watching Science Max Experiments at Large.
Where were the stairs? Yeah. Oh, never mind, I found them.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
like that sound? Does it sound like music?
Sounds good.
Stop!
Yeah.
Yeah.
Yeah?
Yeah.
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 Word has lost all meaning.
Science!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about earthquakes.
Exciting.
How do we build something that won't fall apart when shaken? Plus a lot of other ways to shake things or build things.
Science!
All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large. Today, we're going to be looking at earthquakes. Earthquakes! Huh. Today, we're going to be looking at how to build something. That was supposed to happen earlier. Today, we're going to be looking at how to build something that stands up to the shaking of an earthquake. Earthquakes happen when two plates on the Earth's surface rub together, and it causes the ground to shake. It causes the ground to shake. Sometimes it shakes a little, sometimes it shakes a lot. Chances are you do not live in a place that has earthquakes. But if you do, ask an adult what to do during an earthquake so you can be safe. Modern buildings that are built in earthquake zones are designed to withstand the shaking. But how do scientists and engineers build a building that stands up to the shaking of an earthquake? Well, that's what we're going to be looking at today. First thing we have to do is simulate an earthquake. We're going to build a shaker table. And here's what you need. 2 books and... 2 books, 4 elastic bands, and 4 rubber balls. Oh, wait. Okay. 4 rubber balls. All right, so the first thing you do is actually take your 4 elastic bands and wrap them around your books. Put 1 set on one side, 1 set on the other side, till you have that. Then you take your 4 balls and you stick them in between the books in the middle-ish area. But you don't want to have them too close to the edges. And now 2 at the back. And ta-da! You've made your own shaker table. What are you shaking, you ask? I will show you. You build a tower. Like this one here that I built out of building blocks. So here's what you do.
You'll need your base to be securely attached to the shaker table. I use painter's tape because it'll come off again without harming the books.
And what I want to find out is just how much shaking this tower can take before it falls apart. Ready? Oh. And there it goes. And when you've done that, what you do is you be a Science Maximite and you design another tower. And you tape it down to your shaker table and see if you can make this tower fall down in an earthquake. And if you built it really well, probably won't. But you don't have to just use building blocks. There's all kinds of other materials you can use. Check out this building, which is really tall, and you'll see there's a cup at the top, and that's for a baseball. Put it up at the top, and that means there's a weight up there. And then we shake it, and we see what happens. Oh no! Oh, there it goes. So that is what we're going to be doing today on Science Max Experiments at Large. We're going to be making a giant shaker table and putting a giant structure on top and seeing how we design it to make sure it stands up to the shaking of an earthquake. I'm going to need an expert to help me, though. Oh, I know. Anne would be really good at this. Okay, all I need to do is get Anne, and we can start.
come on. There it is. All right.
Hey, Ann, I feel weird. Why do I feel weird?
I think you're a chair.
Well, that's not good. Hold on a second.
Am I good? Okay. Hi, Ann. Good to see you. Here's your lab coat.
Thank you.
So you're from Let's Talk Science, right?
I am.
All about science education, just like us. Today, I need your help to max out our earthquake table. This is the table
This looks
part,
great.
obviously, but this is a tower I've made out of popsicle sticks. So in order to max it out, I've already built a large shaker table. Come on.
This is my large shaker table. So it's got basketballs underneath as the 4 balls, but it works exactly the same.
Whoa. Okay, so what kind of tower should we make for the shaker table?
If we want something tall, then we'll reinforce it a couple spots. But the true test, it's got to have some sort of weight on top so that it will mimic the weight that would be on a real tower.
Right, so maybe I could get a plastic bin and I'll just put some sandbags for weight inside.
That would be perfect.
And then balls, so that when it falls over, the balls will go everywhere.
That would be perfect.
Okay, great. Shake off. I don't know. I think we should just get off.
Another thing that happens during an earthquake is soil liquefaction. Liquefaction means something turns to liquid. In this case, the very ground you might be standing on. Here's how you can experiment with soil liquefaction. All you need is a plastic container and some water, not very much, barely enough to cover the bottom of the container, because what you're gonna put in next is sand. And you wanna put it in there and spread it around. Just add enough sand so it just starts to turn dry on the very last layer. So here is a house that I'm going to put on top. And now I will simulate an earthquake. The water rises up and it sort of turns to liquid. Soil liquefaction. And heavy things like houses and cars, they tend to sink like that. And then the soil rehardens and everybody's houses are stuck in the mud. Now, let's max it out. This is a giant tub of sand and water, and this is a vibrating platform that will simulate an earthquake. Now, as you can see, this sand is totally solid. I can jump all around on this sand, no problem. But when I turn on the vibrating table and simulate an earthquake, things will change.
The vibrations bring the water below the sand to the surface and cause the sand particles to separate. What was solid now turns to liquid in my simulated earthquake, and I start to sink.
I'm up to my shins! And there you go, soil liquefaction. Hey, look at that. It's totally solid. Woo-hoo-hoo! Soil liquefaction! I'm totally... Uh-oh. You know what I realized? When it stops vibrating, it really becomes solid again, and it's very tough to... Well, there you go. Soil liquefaction. I'm really kind of stuck in here.
So Ann and I have made a large shaker table. Now it's just a matter of designing a building. We use lumber and cut it up, use screws to attach it all together, put a platform on top for a weight, and attach it securely to our shaker table. The building is super simple, just 4 corners and a few planks around the outside. No structure in the middle. And finally, the big heavy weight on the top.
There.
We attach a pole to the shaker table so we can shake from a safe distance and try it out.
Okay, very slow.
Forward.
Let's see how much shaking it can stand with our shakeometer.
That seems to be okay.
Kidding.
Oh no.
We barely start to shake our tower before it collapses.
Oh, that didn't really last very long, did it? It completely folded up on itself. What do we do to fix this, make it better?
I think the easiest thing we can do is to use thicker wood. It'll make it less wobbly.
Okay, sure, let's make another one. High fives. We do have lots of wood, that's a good thing.
Anne and I are trying small improvements every time.
There.
Our last building used thinner pieces of wood. Now we're using thicker wood, which we think will help keep the weight at the top from collapsing the building. Everything else about the design of our building is the same. We put the weight on top and fix our pole, and we're good to go.
All right, you ready?
Okay. Starting to creak.
But it recovers. You can see it lean, and then it comes back, and it resets.
Definitely doing better than the last one.
Oh, no. I'm impressed.
Uh-oh, here we go.
But it definitely did better than the first one.
It did better than the first one.
And the thicker wood definitely helped.
But it was really starting to turn.
I think on the next one, we need some platforms in the center to help strengthen it even more.
Earthquake Building 3.0. Thicker wood this time, but with platforms in the middle.
So we're gonna see how well this version works with these middle parts that'll hopefully reinforce.
And they're just like the floors of a building.
Okay, well, let's find out if it's gonna make any difference.
Starting to wobble a little, but it looks pretty good.
As soon as we start shaking, it's really obvious this building is more solid.
Uh-oh, starting to creak. Oh, it's really starting to creak.
The platforms in the middle really seem to improve the structure. You can see it bend all the way over and still recover. But still, it wasn't long before...
Really starting to lean.
Wow, the extra pieces really kind of made it more impressive.
It definitely lasted a lot longer than the other two.
It did, but here's what I'm wondering. Are we going in the wrong direction?
What do you mean?
Well, because if it's really solid, it resists the change.
Okay, I see where you're going with this.
So if we make it flexible, it can resist the shaking of an earthquake.
I think it's worth a shot.
Yeah, okay, let's do it.
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. My tuna fish and meatball sub soup is coming along quite nicely. But what will we have for dessert? I know. How about earthquake buildings? Ha ha! It's a building made out of wafer cookies. But the people on Vanilla Street built in the gelatin neighborhood. And the people on Chocolate Street built in the crispy rice part of town. Exciting. Now, here comes the earthquake. Oh no! Oh, it's shaking! Oh, the shaking is come and gone for the people on Chocolate Avenue, and their building is still standing. Now, let's take a look over here on Vanilla Street, and here comes an earthquake. Oh no! Oh dear! Looks like the people on Vanilla Street are going to have to rebuild their building because it's all fallen over and being eaten. Delicious. Buildings can be built the same way, but the kind of soil they sit on make a large difference if there's an earthquake. Shaky, wiggly soil or solid, non-moving soil. So there you go, an experiment you can try at home. Delicious. Well, I'm Buster Beaker, and thank you for joining me on this episode of Cooking with Science. Now to try my soup.
Seismometer in 60 seconds!
Learning how to predict and measure earthquakes is an important branch of science. The Earth is shaking, but which way did the earthquake come from? It's all about measuring the vibrations, and to do that, you need a seismometer. All you need is a ball, some paper cups, some modeling clay, a pencil, and science tape, which is the same thing as invisible tape, except I use this tape for science. First, take your pencil and stick it straight down into the modeling clay. Then, you take your cups and you arrange them in a circle and tape the cups down. And that goes right in the middle, just like that. Now what you do is you take the ball and you carefully balance it on the pencil. Now you have created a seismometer. It will tell you what direction an earthquake came from. Watch, I will be the earthquake. Ready? Did you see that? The ball fell into the cup facing the direction that I hit the table. And now I'm gonna hit the table from over here. Yep, it fell in the direction that I hit the table. Okay, let's try from over here. There you go, your very own seismometer that you can use to measure earthquakes that you create on the table.
back to our earthquake building. Anne and I tried a few different designs, and they each got a little better. But now we're wondering what would happen if we built the tower out of very flexible material. We used some plastic tubing and attached the wood with bungee cords, which are like big elastics.
Wow, okay, so looks good.
So let's test it.
Okay.
And sure enough, when we start shaking it, the tower holds up to as much shaking as we can give it.
Wait,
What?
aren't we missing something?
Oh. Yeah, we're missing the weight at the top. Of course.
So I think we need to try it again.
So we add the weight to the top, and then everything changes.
Oh, no.
Look at it twist.
Oh, dear.
It's twisted. It's
A
gonna
flexible tower is great until you try to put a weight at the top. And then it just seems really unstable.
Oh, look at that. It's totally bent.
It didn't break at all, it just fell over.
Yeah, it couldn't even support the weight.
So it was almost too flexible.
So I guess we should go back to a more rigid design. But what if we change the shape a little bit? 'Cause you know what I was thinking? This is a very stable shape. Triangle, because triangles are really strong. What about we make an X?
Like a triangle within a triangle.
Triangle, and then triangle. So that really reinforces all of the shaking, like all of the motion.
We'll never know until we try.
All right. Uh-oh. I have all my friends coming over, and I don't have a table.
But that's okay. I will make a table using my friends.
This is an awesome experiment you can do with 4 friends. Come on in, science friends. I've got Sam and Dylan and Polly here to help me. So everybody turn to your left and sit sideways on the chair, and then scooch the chairs into the middle. And then everybody leans back onto the knees of the other person. And then this is why I said you need 4 friends, because you need the 5th person to remove the chairs. Whoa. The reason why this works is because everybody's weight is being supported on the legs of the person next to them. Okay, we're gonna rotate in a circle, everybody. Okay, ready? Here we go, rotating, rotating. Oh, science table. Ooh, hey, we're pretty good at this. Okay, uh-oh. Oh no, oh no! So there you go. Awesome way to make a table using your friends. Well done, science. Here's an experiment you can do to impress the adults in your house. You need 3 glasses, all of equal height, and 3 knives, not sharp knives, the dull knives you use, maybe the ones you use at dinner time. Take your 3 knives and put them in a triangle, all equally spaced out. Then move the knives together to make a little triangle, right like that. Then what you want to do is you want to carefully arrange the knives so each knife is going above one knife and below another knife. So there we go. Then you want to take this careful pattern that you created and you want to put it on top of your 3 glasses. One where each handle of the knives are going to be. And if you place it carefully and you've done the over-unders correctly, it will stay up. Pretty amazing. The knives support their own weight. But they don't just support their own weight, they can support a lot more weight too. Pretty amazing, right? This is a great experiment. It's also something really interesting that we can max out. Come on. And here you go, the maxed out knife balance. I've got 3 pieces of lumber and 3 barrels, and as you can see, the pattern is exactly the same. Under, over, under, over, under, over. Ha-ha. So, the question is, how much faith do I have in science? It totally supports my weight. I know it's going to work because I know that a 2x4, which is the kind of lumber I'm using, can hold up my weight. So that means the structure can support me. Science! You know what the cool thing is? The cool thing is that even though it's holding me up, each one of these pieces of wood is only up because it's supported by the others. You pull one out and it all falls apart. Anne and
and I have tried solid towers and flexible towers, and nothing has worked fantastically yet with a big weight on the top. Having a big weight on the top of our tower means we need something that will resist the movement of that weight. So now we're going to start with a triangle. Unlike a rectangle, triangles are very stable. A wider base keeps the structure from swaying too much. And cross braces in the middle mean that there are other triangles within our triangle, all the better to resist movement.
Thank you.
After Ann and I built our tower, we added the weight to the top, secured it to the base, and tried it out.
Okay, here we go.
Looking good.
No problem.
It's not twisting.
It's
Not leaning.
not even creaking.
No, it looks really good.
Wow, this one is really solid. As you can see, this tower is way more solid than our square tower or the flexible tower.
Okay, look at that. Like, if that's not an earthquake, I don't know what is. Look at that. Look at the way the ground is moving.
I don't know if we can shake it much more than this.
Faster.
Our triangular tower is up past a level of shaking that made the other towers collapse. Now it's time to max out the shaking.
There's only one level of shaking that we can do above this.
What's that?
We shake from either side.
We give it all we have. The floor was bouncing from side to side, the tower was tilting, and was totally solid.
It's still holding strong.
In fact, Ann and I wore out before the building showed any signs of falling over.
I think we've done it.
Woo! Nice job.
Nice. Science Max Experiments at Large earthquake-proof building. I mean, come on. That was impressive.
I like it.
Here is an invisible tower. Huh? Ha 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 ha. I escaped.
I'm just preparing I forgot my line. Hello. Just gonna add some more salt to the soup. Delicious.
Well, humans have been figuring out ways to figure out just that. I said figure out twice. I'm gonna start again. Okay.
English is not my first language.
I guess those are staying in there.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Newton's third law is the science behind balloon-powered rocket cars. It's also the science behind a maxed-out rocket car that I can ride. Plus bowling balls and an interrupting sign. Today on Science Max, Experiments at Large. Greetings, Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the balloon-powered car. Here's how it works. Woohoo! It all has to do with Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
We don't have to do this now. This is all for later. We can build the cars first, and then we can, let's go over here. So how do you build a balloon-powered car? Well, I suggest you be Science Maximites, because there's any number of ways you can build a balloon-powered car. You do not have to follow my design. You should come up with one of your own. It may even be better than the one I built. But I will give you some tips, though, that make it a lot easier. First of all, you need something to stick your balloon on that has an opening on it. I used a turkey baster for this car. I just pop the top off, and remember to tell an adult that you're using the turkey baster. And then you stick the balloon on there, and it allows you to attach something to the car, and it also makes it easier to blow up the balloon. You can use any number of things, even just any kind of tube that you find lying around. It helps you attach the balloon to the car, and it helps you blow up the balloon way easier. The other thing you should think about when you make your balloon-powered car is how you're going to make the wheels roll. Once you've decided on the base of the car, you could use anything, even just a piece of cardboard like this. You can do your wheels in two ways. The first way is to attach the wheels to the axle.
This is how I made the axle of this car. I used a shish kebab skewer, and I stuck it inside a straw, just like that. And then I attached the lids to the shish kebab skewer. So the lids and the shish kebab skewer are attached and they rotate in the straw. That's one way to make the wheels turn. The other way is to tape down the axle or whatever you're going to use and have the wheels spin around on the axle. Two great ways to make your wheels turn, and it really kind of depends on the wheels you're using. You can make your own design and keep refining it and making it better and faster, or do what I like to do and make a whole bunch of different cars. So we've got this one. This one I made out of paper plates, and this is a snorkel. Awesome. This one is the rock car, because there's a rock on it. I've got the dragster model. It's a long broom handle, and it might not work that well, but who knows? And this is my favorite design. It's made out of waffles and an ice cube tray. This is why I make a whole bunch of different cars, because I can race them.
Sunday at the Science Maxodrome. It's the balloon-powered car winner-take-all drag race of awesome.
First up, the Eliminator.
Woohoo! Better late than never, it's the Procrastinator. Crushing the competition, it's the Terminator! Feel the chill of the refrigerator. And last but not least, the, regurgitator!
Well, when you build your balloon-powered cars, you can figure out what worked or what didn't work and try modifying your designs to make them work even better. That is science. And now we're gonna max it out, because this is Science Max Experiments at Large. So we're gonna take that small balloon-powered car that we just built and we're gonna make it much, much bigger. I'm gonna go to the Center for Skills Development and Training, and we're gonna use the science behind the small balloon-powered car, and we're gonna make it big. That science is Newton's third law, but there's plenty of there's plenty of time for this later. We're not doing this bit now. We're doing that bit in a minute. So we could, no, I said we're doing it later. We're doing it later. Here. Whoa. Hi, Sarah.
Hi, Phil.
This is Sarah, and she's got a master's degree in physics from McMaster University.
That's right.
And we're gonna be talking about Newton's third law. Oh, look out, duck. Sorry. There was a sign that kept coming in. Never mind. Newton's third law. Well, what is that?
For every action, there's an equal and opposite reaction.
Right. So how does that work with our balloon car?
Ah, cool. Okay, so if you blow up the balloon, what's gonna happen when you release it is the air is gonna push out with a certain force, which in turn is gonna cause the cart to move forward with the exact same force.
Yeah, works great. So how come it doesn't work with my rock car?
Ah, wow. Well, actually, it did work. So the balloon still pushes with the exact same force, which causes the cart to have the exact same force push forward, but your rock is really heavy, so you probably didn't see it move.
Oh, so a lighter cart works better with the same amount of force.
That's it.
Well, there you go. Newton's third law. What?
Newton's third law. For every action, there is an equal and opposite reaction.
I'm really starting to dislike that sign.
Phil, are you okay?
Yeah, I'm fine.
Our small balloon-powered car works because of Newton's third law. For every action, there's an equal and opposite reaction. The air pushing out the balloon this way pushes the car with the same amount of force this way.
So, in order to max it out, the plan is just to get a bigger wheeled cart and a much bigger balloon. So, everything should work out the same.
Okay, so I thought what we would do is in order to max out the balloon-powered car, what we need is a cart to start with, and then I ride it. And we have a giant balloon, and then I go.
Do you have a giant balloon?
Ha 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 ha! Giant balloon! So, step one, Sarah blows up the balloon.
Okay.
Wait. Use this air compressor, it'll probably be a lot faster.
Sarah and I get to work blowing up the balloon, and it takes a long time. A very long time.
Okay, human-sized balloon-powered car test. Take one. All right, Sarah.
You got it?
Yeah. Okay, let it go.
Okay, go.
Let it go.
I did.
You did let it go.
I let go.
Nothing is happening.
It's not coming out fast enough, and you're a bit too massive. I don't think it's gonna work like this.
Really?
Yeah.
Okay. Balloon-powered car test 2. No fill. I'll just take it. What happened?
I don't think it worked. The balloon popped. Phil, are you okay?
This is why you wear protective eyewear. Yeah. So, that didn't work.
No.
No. Should we get another balloon?
I think we need something else.
Okay, well, the air coming out of the balloon just didn't have enough force, so.
We need the air to come out with more force.
Yeah, do we get, what, a bigger balloon?
I don't think that's gonna work. I don't think it's that. I think we need something with compressed air.
Oh, like a scuba tank or a...
Fire extinguisher, something like that. Yeah, that's what we need.
Okay, sure. Well, we can... All right, so I don't know if that's safe to do that, so we'd have to build like a cage or
Yeah,
something?
I don't know if it's gonna work on this.
All right, well, back to the drawing board. So
Okay.
what we should do is we should get
We need to find these tanks.
get the tanks, and then we make like a frame out of aluminum or something.
Okay, that could work.
Yeah,
That's
they
a
can
good
hold the
idea.
tank, so
Yeah.
they're safe. And then what we should do is...
Who was Isaac Newton? He was a mathematician and probably number 1 on the list of top scientists of all time. Albert Einstein said, Isaac Newton was the smartest person that ever lived. You've got to be special if Einstein is calling you smart. Newton's 3 laws of motion was a huge idea, but did you know Newton also came up with the idea of gravity? The famous story is that in 1666, Isaac Newton was sitting under an apple tree when he watched an apple fall and wondered why. Hey everyone, I just invented gravity, which was a big relief because up until then, everyone was just floating around. Okay, so it didn't happen like that. He didn't invent gravity. He gave a name to this invisible force and then described how it works. Not only did it make things fall down, but it was the same force that kept the moon circling the Earth and the Earth circling the sun. And he invented a new kind of math to explain how. We now call it calculus. See? I told you he was smart. He's very smart.
This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be Science Maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out. I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet, and half of me is dry. What's more, half of my outfit ended up being wet, and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool and I realized I should have duct taped the pocket because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out, now it's keeping the water in. Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back.
When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction.
Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's, well, it's really easier to see if I'm not standing on the ground. No, hold on. Okay, so, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's
third...
No, hold on. Newton's
third law.
Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
So, using a giant balloon to push me on a cart didn't work.
What happened?
The plan now is to use the compressed gas cylinder. Just like a balloon, these cylinders contain a lot of air. If we get a cart and put a gas cylinder in a cage for safety on the back and open the valve, the escaping air might have enough force to push me.
This is 2 cubic meters of air. If we were to put it in a balloon, the balloon would be this big. But if we compress the air, we can fit it all into one of these, a steel tank. This is what we're going to be using next for our air-powered car. Got it?
Yep.
All right.
Good.
So Sarah and I have been hard at work, and we've built the air-powered cart. We can't call it a balloon-powered cart anymore because now we've got a compressed air tank, so it's not a balloon that powers it.
Exactly.
Okay, so I'm gonna sit on here, Sarah's gonna turn on the tank, and I'm gonna go. And before we do this, we should say, do not, under any circumstances, try this at home. We are trained professionals. You ready?
I'm ready.
Okay, high five first. Okay, now we do it.
Okay, so before I turn the tank on, make sure your feet are down and the brakes are on.
Gotcha.
Don't take them off till I say go.
You have got it.
All right.
Ready?
Okay.
Yeah!
It worked!
Yeah, it did work, but I feel like it could work better.
You want to go faster?
I do want to go faster. This reminds me of the rock car.
Yeah.
Where we didn't have a big enough balloon.
We need more force.
We need more force. So should we get a bigger tank?
Let's get more tanks.
More?
Tanks, more force. You're gonna go faster forward. Newton's third law.
Newton's third law, high five. All right, let's do it.
All right.
Whoa. Okay. This is Newton's cradle, and it's a really cool toy that demonstrates all kinds of laws of motion, including Newton's third law. What you do is you pull this one ball out, and when it hits these balls, they exert force on that ball to make it stop moving, but it exerts force on these balls, which travels through the balls and makes this one on the end fly out, like that. Now, there's a lot going on here, but you can really see how the force is equal that you put in and you get out if you use two balls. I swing two balls up, and two balls go out that side. Isn't that cool? Now, it wouldn't be Science Max unless we maxed it out, so come on. Whoa, okay. This is one we built out of bowling balls. Bowling balls. Bowling balls. Instead of smaller balls, and I think it's gonna work the same way. Let's find out. You throw one out, and yeah, it works the same. Okay, now let's try it with two balls. Okay, ready? Wait. And two balls, throw them out. And two balls on that side. All right, so there you have it. Whoa. Newton's third law. Oh.
Newton's third law. For every action, there is an equal and opposite reaction.
So our single pressurized tank created enough force to move me, but not very fast. The plan now is to do two things. First, we're going to triple the amount of thrust by using 3 tanks. We're also going to use some pipes that lock into each other to give me an initial push. These pipes slide together, and when the air is turned on, the pressure in the pipes will cause them to slide apart, which will push me forward. After that, I use what's left in the tanks to keep going.
All right, now it's time to max it out. I've enlisted the help of a few more Science Max people. Thank you very much, Corey. You'll see now we have 3 tanks of compressed gas, and we've also got this nifty little contraption. How does this work, Sarah?
All right, so each tank is attached to a tube, and you can see that each tube goes into this one main tube, so when we turn them on, pressure's gonna build up, and we're gonna go forward with more force.
Well, that's great, and Reed is stacking cinder blocks, thanks Reed, up so that will push, the pipe will push against the cinder blocks, and then I'll go that way. All right, well, are you guys ready?
I'm ready.
All right, let's do it. Now, again, I have to say, thank you, Corey, I've got it. This is something you definitely don't want to try at home. We are all trained professionals. We have a physics degree here. We've got TV people that make sure that this is safe. So watch it and enjoy, but please don't try any of this at home. Okay, I'm ready. Sarah, count me down.
3, 2, 1.
That was awesome!
That was really awesome.
All right, high fives, high fives. Yeah. And it's raining now, so it looks like we're gonna have to stop. So thank you very much for joining us on Science Max Experiments at Large in our episode on Newton's third law.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Wait, I can play Mary Had a Little Lamb. It's working! It's working! Newton's cradle out of bowling balls. Come on! You know this one, sing along. Whee! Come on! I mean, come on! Science! Yay!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about building things strong. 2,
And let's do 3.
an arched bridge, giant house of cards, magical stacking books, and more.
Oh, I thought they were gonna do it.
All on this episode of Science Max, Experiments at Large.
Oh, hello, Science Maximites. We've got a lot of work today, so I was just getting prepared. You know, taking something flimsy and making it strong, that's what scientists and engineers do every day. And it's also pretty fun. You take something that's not that strong, and by the way you build it or put it together or change its shape, it suddenly becomes a lot stronger than you think it was. So I thought that's what we should do today on Science Max Experiments at Large. We should build something. So we're gonna build an arched bridge, and we're gonna build it out of sugar cubes. So here's what you need. You need some sugar cubes, you need some sandpaper, and you need some modeling clay. So first, you want to make some abutments out of your modeling clay. What is an abutment, you ask? It is this. They distribute the force laterally from one side or the other. I like to use this. This is half a roll of duct tape. And so it fits in just like that. And you see, it's a perfect arch. If you just take sugar cubes and you try to stack them into an arch, it's not going to work because the sugar cubes may not even fit all together, and you can see only the bottoms are touching. I take up the guide and it all falls apart. So here's what you do. You take your sandpaper and you change the squares into trapezoids, and you start sanding down your sugar cubes into trapezoids. Basically, you want one small side and one long side. Thin at the top, wide at the bottom, or wide at the top, thin at the bottom. It's a trapezoid no matter which way you hold it. Put it on the bridge and see. And as you go, you will see if you're doing it right, there will be no gaps. If you go to the Science Max website, there will be a guide that you can use to help you make the sugar cube bridge, so you don't have to spend as long as I did making this one. And then the most important part is the keystone. That's the one that fits in right at the top, just like that. And when it does, you can take away the guide and it stays up. Isn't that cool? It stays up without any glue, without any mortar, all based on the shape of these sugar cubes. The cool thing is, it'll hold the weight of a whole car, provided you have a very, very small car. The reason why it works is because the weight is distributed along the arch into the abutments and down into the ground. That's what makes an arched bridge so strong. And that's what we're gonna do today. We're gonna max out an arched bridge. So I think I'm gonna need some help though. Maybe Sonia from the Ontario Science Center. She really knows her stuff. Yeah, I'll go there and I'll see if she's busy. All right, come on, let's go. Hey, Sonia.
Hey, Phil, how's it going?
It's going good. I was wondering if you could give me a hand with something.
Okay, what's up?
I'm building, well, it's easier if I show you.
All right.
Do you mind coming back to Science Max headquarters? We can take the portal.
But that thing doesn't always work.
Oh, it is fine. Well, I mean, that worked just fine. Uh-oh, it usually makes a beeping when I do, oh, it's out of batteries. Oh, I told myself, Phil, charge the remote before you leave the lab, and then I...
Where have you been? Breathe.
The remote ran out of batteries, so I had to run the last 3 kilometers.
It's all right.
Because
You made it.
Long story. So the Sugar Cube Bridge, you had a chance to look at it, right? This works on any scale, right? It should, no matter what size arch, it should be the same, right?
Definitely.
Good, because what I want to do is use these abutments, but go to these abutments.
Oh.
So I'm going to start the bridge here, and I've already created a thing that we can use to put the sugar cubes on as we go up, so that we can make sure that it becomes a
Phil.
perfect arch. Yeah.
Do we have enough sugar for this?
Yep. I got tons of sugar.
Whoa!
Yeah. So I think we're gonna need some glue because it's gonna be really hard to get these to stay
Yep.
right
on.
there without a little bit of glue. We're gonna make a giant arch, maybe some walls, and we'll see what happens.
Let's do it.
Oops. An egg. Now you might think of eggs as kind of flimsy, and they do break pretty easily, but eggs are actually stronger than you think. It's because they're, well, egg-shaped. You see, the top of the egg is like a little bit of an arch, and the bottom of the egg is also like an arch. And arches distribute the weight, just like they do in a bridge. Here's how you can experiment with how strong eggs are. First, you want to get a pair of gloves to protect your hands from the shell, just in case anything goes wrong. You should also tell an adult that you're doing this experiment because if it does go wrong, you're gonna have some mess to explain. And also, you should probably put on some safety glasses. Now, here's what you do. Take your egg and carefully put it in your palm just like that. And put it against your other palm, and you're gonna push in directly on either side of the egg. Start pushing harder and harder. You can even lace your fingers and press even harder. And if you do it right, the egg won't break. Pretty amazing, right? So, just how much weight does an egg hold? Can one egg support my entire weight? Let's find out. I'm gonna lift my weight up like this and lower myself down. And no, cannot hold my weight. Can my weight be supported by 2 eggs? Oh, nope. Phil's weight, 4 eggs. Oh, I thought they were gonna do it. Nope. My weight on 8 eggs. Huh? My weight can be supported by just 8 eggs. Science! Whoa, careful.
Sonia and I are on a quest to make a maxed out sugar cube bridge. The reason why an arch works is because the weight, or the load, of whatever's on top of the bridge is carried outward along the curve of the arch to the abutments at each end, which carry the load and keep the ends of the bridge from spreading out. No matter what you build your bridge out of, sugar or stone, the science stays the same. Sonia and I are building a much larger bridge out of sugar cubes. We're using glue to help the sugar cubes stay together, just like stone bridges use mortar. And when we're finished, it was pretty impressive.
A massive sugar cube bridge, right? High fives for that.
The moment of truth comes when we take out the support and...
Yeah! It works! Okay. Giant sugar cube bridge. So do you think it'll hold some weight?
I think it definitely should, because right now we have an arch, perfect arch, and the weight is being distributed to the sides, the base.
So that's what it's for, right? We can put weight on there?
We can definitely put some weight.
1 to start?
Let's start off with 1.
Okay.
And let's see how it goes.
All right.
Here we go. All right.
Yeah, 1 book, yeah! All right, sugar cube bridge.
1 book.
2 books.
Are you nervous?
Yeah! Sugar cube bridge, 3 books.
3 books.
Oh, that was great. It held up 3 books.
3.
Well, technically it held up 2 books and broke on the 3rd.
So it's kind of still far from how much weight we want to hold because we want to cross it.
We definitely want to cross it, so that means we need something bigger and stronger. The cube works.
You're right, because the cubes are great because that keeps the science the same.
Yep.
Right? So something cubular. The milk crate, really?
Definitely, I think we should use those. It's a cube.
It is a cube. A whole bunch of milk crates, and we'll see what we can do.
I think that sounds great.
Awesome. Whoa. This is a Prince Rupert's drop.
It's a piece of glass that has a long snaky tail and a bulb at one end.
So what's so interesting about a glass tadpole? Well, I'll show you. And remember, this is just glass. Oh, Prince Rupert's drops are very strong, almost as strong as steel. It's all in how they're made. Molten glass is dropped into cold water.
What happens is the outer part of the drop cools off first, leaving the inner part still hot. When the inner part eventually cools, it contracts, pulling everything in tighter and tighter, keeping it under a lot of tension. And because it's round, the force you put on it is distributed all the way around, just like the force is distributed on an arched bridge.
Until you get to the tail. Just the tiniest break in the tail, and
it explodes. All that energy is released in a chain reaction. Why it's so strong you can hammer on one end, but explodes when you break the other, puzzled scientists for centuries.
But now we know it's all in how it's made.
The Wizard Academy. All you have to do is demonstrate true magic, and you will be granted entry.
Send in the next applicant. Okay, don't let them see you. Don't let them see you. Okay, magic smoke. And here we go. Big entrance.
Behold, it is I, Hoverwhelmo.
You again. I only have to demonstrate magic one time, and you have to let me into the Wizard Academy. And last time does not count. So prepare for your mind to be boggled and your eyes to also be boggled, because I shall do a trick. I will just get to it. Here is a book, behold! And now, feast your stupefaction as I produce another book, ha-ha! And then 2 or 3 more times, behold, that's good. Behold! And now, look upon the wonderment as I stack these books on top of each other, like this. And now, feast more stupefaction as I cleverly move the books off the table. And now comes the magic word. Now, I say the magic word. The magic word! And behold, the book is levitating. It is completely off the table. I have done it. Magic!
No.
No?
Not magic, that's science.
But the book is levitating.
No.
Look, it's not even touching the table.
No, it's being supported by the books below because of the center of mass.
Preposterous.
I'm afraid it's very posterous. Each book is balanced on the one below in a way that the center of mass is behind the edge of the book below. And the entire stack's center of mass is behind the edge of the table. So it may look like magic, but it's science.
So, I can't get into the Wizard Academy?
No, I'm afraid not.
Aye, good. Alakazam! You will rue the day that Overwhelmo did not. I will return, and then you will see. Oh, ow.
Sonia and I made a large bridge out of sugar cubes, and it didn't hold much weight. So now we're going to try making another arch bridge, but instead of sugar cubes, we're going to use milk crates.
There we go. I've made some abutments out of giant crates, and this is where we're gonna start our bridge, and they start there, and it goes in a big arch, but we're gonna be using...
I brought milk crates!
Milk crates! High fives! High fives!
So we start our bridge.
This is a straight line, it's not an arch.
It's not an arch.
But it's clear we have a problem.
Okay, ready?
That didn't work, Phil.
It's like we're back to the beginning again. So this is like 2 straight lines.
We have 2 straight lines,
it's
yep.
like a triangle.
We need an arch, so we're gonna need a support.
Sonia and I build a support to help us make a curve the milk crates can follow. But after we finish stacking, there's a problem.
It doesn't look very solid.
Yeah, it doesn't, does it?
Here.
Oh, yeah. Because there's a gap at the top of all of them. Look, that one, there's a gap. There's a gap there.
There's a big
There's a
one
gap
here.
there.
It's
Well, I
not
mean,
making our bridge very solid.
There's only one way to find out for sure.
You can try it.
Is to pull this out and see if it stands up.
Let's do it.
Okay. so didn't stay up.
Didn't stay up.
Okay.
That's all right, though.
I'm not sure why it isn't staying up. Like, the sugar cubes were cubes.
That's a cube.
Milk crates are cubes.
But we did change the shape of the cube.
Oh, yeah! If you remember, when I first built my sugar cube bridge, it didn't work with cubes. You have to sand the cubes down to make them into trapezoids. You can't build a perfect arch out of cubes.
So they were tall, wider here and then narrower there so that they had... Oh, so that's the problem.
Yep.
So I could, like, cut it? I could cut it. I could cut it.
You could.
I could cut it.
That's gonna take a long time, though.
If we cut the milk crates into trapezoids, everything will work, right? Right? We take a milk crate and with the right safety gear, we cut it so we can reshape it into a trapezoid.
Good.
And it works. But
it's gonna take a long time, isn't it?
Definitely. So how about this? I have an idea. So remember when we did the experiment and we had lots of V gaps?
Yeah?
How about we put some wooden wedges into those gaps to make it one secure structure?
So it was sitting like this.
Exactly. So what we're gonna do is insert wooden pieces right here, so we'll fill those gaps.
I get
and
it.
we'll make it one secure structure.
Instead of cutting all of our milk crates, we can keep the milk crates.
Yep.
And they can be solid and we just add to it rather than take away.
Taken away, exactly.
That is a smart idea. Okay, let's make some wedges.
All right.
Oh, hey, how you doing? Let me guess, you want to build a strong structure, something that'll stand the test of time. Well, you know you gotta use the right kind of shapes. Look at this, a square. Now, squares have gotta be strong, right? Well, maybe. Maybe if you press straight down on it, but watch as I push to the side. Oh no! The thing that I have built is now collapsing because squares aren't in fact strong after all. If only I had listened to Sal's sage advice. Yeah, squares aren't gonna cut it. Fortunately, there's a shape that's strong in all kinds of ways. A triangle. Okay, so you heard of triangles before, good for you. But look at this. You can push down from the top and it doesn't move, or you can push from the side and it doesn't move. Triangles are awfully pointy. How do I build with them? Observe! Ha-ha! Triangle here, triangle there, platform on top. And watch. No matter how I try to shift it, it stays solid. And check this out. Triangle here, second triangle there, and a third triangle shape here. That's like 3 triangles for the price of 2, huh? That's a good deal. So there you have it. The triangle, one of the greatest shapes to build with. This is a house of cards, and if you've never built a house of cards, you should definitely try. Try, because it's not easy. What you need to do is you need to make triangles with the cards. If you do it just right, they'll stay up. Then you take another pair of cards, like that. You take another card, and you put it on top. And it stays up.
keep on building by making triangles and putting another card across the top like a roof.
Then, when you're ready, you can start to make a second layer.
It takes a lot of patience to make a house of cards. But with enough patience and really steady hands, you might be able to finish it.
There we go. Ha-ha, a house of cards. Now, let's max it out.
Shh, backing away slowly. Backing away slowly.
To build our maxed out card house, the Science Max build team and I used large pieces of foam insulation, which were super light and easy to work with. Once we set up the first layer, we needed to bring in a scissor lift so we could keep building the next layers. By the time we got to the top, our card house was 10 meters tall.
Yeah! Giant house of cards! And now that I've built a giant house of cards, what do I do with it? I knock it down. Science!
I'm gonna build it again.
Sonia and I are rebuilding our milk crate bridge. Since cubes don't work if you're trying to make an arch, and changing the shape of each milk crate would take too long, we're using wooden wedges to fill the gaps at the top of the milk crates. Once we get the wedges in, the milk crates have support at their tops, and they make a perfect arch.
Are you ready?
I'm ready.
All we have to do is pull the wooden thing out, and if it holds up on its own, we've done it.
We pull out the support, and
It stands!
it works! The bridge supports itself! Now it's time for the final test.
We try to walk on this bridge.
So we spent some time making sure our bridge was safe. We added a crash mat, and
We built a second arch
We sure did.
so that it's a little bit wider, and it feels very solid. So the only thing to do now is to test it.
Test it out.
You gonna do it?
I absolutely will.
All right.
Sonia puts on a helmet and gives it a try. And sure enough, it works!
Yeah! Milk crate bridge! 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 Woo-hoo-hoo-hoo! Science Max experiments at large. Milk crate bridge!
Yay for science!
High five! High five! There. Not going great so far. Behold! Beginning steps. I see a problem. Look, I can spin it on my finger. Ow!
I was wondering if I could ask you a question.
Yeah, go ahead.
What? Do your hair like that?
Well, you don't like my hair?
Well, it's okay, but you know, what if you parted it to the other side?
Huh.
Never thought about that. Maybe I should try that. Well, I would say, Henry, that bridge is sure sugary.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Electromagnets are magnets you can turn on or off when you want. We build our own electromagnet and see just how powerful we can make it.
It held 100 kilograms.
Plus ferrofluid, wizards, and I tried to get to the North Pole using a compass.
Now that I'm here, I realize it's really difficult.
All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. At this very moment, half the lab is being held together with the power of electromagnets. And Magnet 1 turning off. Electromagnets are a really cool and powerful way to interact with the world. And when I say power, that's because you need power to make them work or not work. Magnetism is an invisible force that has to do with the magnetic fields created by magnets that lets them attract things that are metal or each other. But electromagnetism is a little different. You see, magnets are magnets all the time. It's because of what they're made out of. Electromagnets are only a magnet when you have an electric current going through them, which means you can turn them on or off. Today, we're gonna be building an electromagnet. Oh, that was the wrong switch. Anyway, like I was saying, today we're gonna be building an electromagnet.
You need a bunch of copper wire, a very large nail, or something metal to become your electromagnet, electrical tape, a battery, an on-off switch, wire strippers or a craft knife, and the help of an adult, and finally, something to magnetize, like these paper clips. And remember, all of the steps for this experiment are on the website. To begin, take the copper wire and start at the top of the nail. Leave a little bit of wire sticking out, then carefully start to wrap the wire around the nail. Don't go all the way to the end because you need some metal to turn into the magnet. Instead, when you want to start again, run the wire straight back to the top and start wrapping again in the same direction.
And keep wrapping and wrapping until you get to this. Now, I've used some electrical tape here, here, and here to hold it all together.
Using your wire strippers or a craft knife and the help of an adult, remove the plastic coating from the ends of the wires. Attach these wires to the wires from the on-off switch with electrical tape, or attach them directly to a battery if you don't have an on-off switch.
And ta-da, you have an electromagnet with your on-off switch. All you need to do is take the things you're going to magnetize, turn your electromagnet on, and suddenly it becomes a magnet. Pretty amazing, ha 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 ha. And then you can magnetize to your heart's content. But when you're done, don't forget, you want to turn it off. So that's what we're gonna do today on Science Max, Experiments at Large. We're gonna max out the electromagnet. So, where's my lab coat? Oh, there it is. We're gonna see how big we can make an electromagnet. And when I say we, I mean me and an expert. Let's see. Oh, Heather from the Ontario Science Centre. She knows her way around magnets. So let's see. Yeah. I wonder if she's busy. Well, let's find out.
And after we're done, I'll need to come back and clean up the giant mess I made in the lab.
Hey!
Hi, Heather, how you doing?
Good to see you, Phil.
I was just wondering if you could help me with something. Are you busy?
No, I got time.
Okay, great, because I'm gonna make a giant electromagnet experiment and I need your help.
That sounds like a lot of fun.
Okay, great. Let's go back to Science Max headquarters.
Oh, via the portal?
Yeah, by the portal.
Oh, okay.
You sure?
I
know you're hesitant, so I want to reassure you, nothing will go wrong.
Great, okay.
Okay. Oh, hey, we're here.
We're outside.
It's okay, it's
no,
okay. Don't worry about it.
No, I think
It's
definitely.
fine.
You all right?
Yeah, I was supposed to come in over there, but I came in over here. Oh well. So today, Heather, I want to max out the electromagnet. Turn it on, and it's a magnet.
Pretty good.
And turn it off, and it stops being a magnet. I want to make this into a much bigger, maxed out version.
All right.
So what are some of the things we can do to do that?
Well, actually, if you have a larger battery, one that has a higher voltage, we can try that for sure.
Okay,
that
so
will help.
there are batteries that are 12 volts?
Yes.
We could try one of those?
Give it a try,
I think
for
those
sure.
are like bigger, right?
Yeah, bigger, more powerful, absolutely. Now, that's one thing you could do. You can also increase the number of wraps of our coil here.
So how many times we wrap that wire?
Yes, we'll increase that magnetic field, making our magnet stronger.
And of course the nail, which is important because that's the thing that eventually becomes the magnet, right?
Right on, yes.
So what I thought we would do is we would start with a bigger nail.
Oh.
What, right? So larger battery.
Yes.
More voltage and a lot more wraps of the wire.
Right on, and we have more space for that now, which is smart. Good job.
Great, okay, so we'll get to work.
Great.
Max Historica.
If you've ever seen a compass, you know that the needle points north. That's because a compass needle is a magnet and it points towards the Earth's magnetic North Pole. And I'm using this compass to try to get to the North Pole. But it isn't easy. In fact, scientists knew there was such a thing as the North Pole as far back as the 16th century, but no one was able to actually get there on foot until 1927. You'd think it wouldn't be that hard, right? I mean, the needle points you straight there. Just follow the needle, right? But now that I'm here, I realize it's really difficult. I mean, the wind is incredible and the snow is intense and it's so cold. My hands, yeah. So, okay, we're not really at the North Pole. We were just sort of recreating that. But still, I salute the brave explorers who tried to make it there in the name of science. And I got a sense of it because the wind from the fan and the fake snow was. Okay, everybody, let's pack it up. I mean, that was pretty good. I just didn't know about that other camera.
So, back to our main experiment, where Heather and I are building a larger electromagnet. An electromagnet works like this. When an electric current is traveling through a wire, it creates a magnetic field. If you wrap that wire around something ferromagnetic, that's something made out of a metal that is attracted to magnets, like an iron nail, then it becomes a magnet. You can make a magnet stronger by wrapping more wire, which gives more distance for the current to travel, increasing the magnetic field, and you can also increase the strength of the current. Heather and I start with a coil of 30 meters of wire and start wrapping. And wrapping. And wrapping.
There, the wire is now all done. And remember, if you're doing this at home, do not use a drill unless you have an adult to help you out, because drills can be very dangerous. This one goes at a very slow speed, so it was okay. But yes, definitely an adult supervised activity.
Then we attach another on-off switch and make some leads that connect to a 12-volt battery. So, more wraps of wire and more current means the electromagnet should be stronger.
Okay, so we're gonna try this electromagnet, and we're gonna pick up this stuff right here.
Great.
Ready?
You ready?
Yeah.
3,
2, 1, go! Is it on?
Yeah.
Wow, it really does, you can't tell it's on, but...
No, but bring it closer and...
Oh yeah, look at that. Okay, we turn it off.
All right.
Let's see if this nail can pick up this nail.
All right.
Ready?
Ready?
Go. Oh. Okay, how about this side? Oh, no. No.
I don't think we're strong enough.
It's not strong enough. I think that we need to max this out even more.
Even more?
Right.
So I'm thinking there are a lot of appliances that use electromagnets, meaning it's already set up, it already has tightly wound coils and high voltage. So we're in a lab here. Maybe do you have old appliances around?
I have parts bins with a whole bunch of stuff. Maybe we could find some electromagnets in those.
Let's do it.
Okay, great.
Yeah.
Let's go. All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need.
A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers.
So here's what you do. First thing is you put the batteries and the magnets together like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here. And if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So, now, let's max it out. Aha! A D-cell battery, which is larger, and of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and ha-ha! It spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I take the copper coil. I need to get. Okay, hold on. I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work, but that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement.
Heather and I built a larger electromagnet, but it still wasn't as powerful as we hoped. So now we're searching for parts that came out of an appliance that are pre-built electromagnets.
What about this?
I think that'll do the trick.
Do you think that does look like an electromagnet, huh?
It does, yeah.
And there's a whole big bunch of copper wires coiled on that.
Around.
So you think we can use this?
Yeah, let's try it.
Okay, great.
We built the next version of the electromagnet. This one already has the copper coils, so it's just a matter of attaching wires and an on-off switch, and attaching all of it to a 12-volt battery.
Do you think 12 volts will be enough?
Let's find out. I think so.
Try that.
Once we do, it works much better.
Oh, no problem at all.
Ready?
Yep, turn it on.
On.
Whoa, pretty good. Okay, off.
Off.
Neat. In case it was really strong, I have the next step. Horseshoe. Okay, ready? Oh, whoa, that's...
Here.
I can't pull that off. Okay, wait, grab this. Okay.
Work together.
Yep.
Wow.
So that's passed all of our tests.
Yeah.
This is really strong.
Is there a way to test it further?
In order to test how strong our magnet is, it's as easy as seeing how much weight it'll lift. Heather and I find a metal table.
All right, Phil, so I brought the electromagnet.
Okay.
Just put it right here.
Yep. We add some sandbags for more weight and then attach a scale so we can measure how much weight we're lifting. We use a chain hoist, a simple machine made for lifting heavy things. This one can hold up to 454 kilograms.
Want to turn it on?
We're ready?
Yep.
Here we go.
You can read on the scale how much weight is being lifted.
And that scale is going up.
Pounds on this side, kilograms on this side. We keep lifting until...
Oh, okay, so how much did it hold?
It held 100 kilograms.
Oh, that's more than I weigh, which gives me an idea. Come on.
This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top. And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science.
The Wizard Academy. All you have to do is demonstrate true magic. And you will be granted entry.
Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo.
Indeed, it is I, Overwhelmo. And prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end?
Not really, no.
But would you be impressed if I was to balance this coin on top of this coin?
Possibly.
Prepare to be flustered and stupefied. stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Hoverboard. You can do this.
And now, I say, a magic word. A magic word!
Ha 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 ha! And now you must let me into your academy. Wait. What's under the cloth? What cloth? This cloth? Nothing!
Oh, is that a magnet?
This? No!
The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling.
No, this is set dressing. It's just...
It was a good trick, but it's science, not magic.
Well, yes. And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks. Because I will knock them off! With my magic, you will need at least 2 pairs of socks, maybe 3 pairs of socks.
We can still see you!
No, you can't!
So back to our main experiment. Heather and I have created a very strong electromagnet that can hold a lot of weight.
It held 100 kilograms.
Oh. Which gave me an idea.
All right, you ready?
Let's do it.
Electromagnets, super maxed out experiment. We've got
2 electromagnets, 1, 2.
And those are wired to 2 batteries, which are on my belt, just like this, so that I can carry them around. And we've got a crash mat here, because...
We need to keep you safe because you're gonna be using these electromagnets to get across this massive beam above us.
That's right. I'm gonna stick to this metal beam and go across with the electromagnets.
Wow.
We hope.
I have faith.
I'm glad you do. I've got helmet for safety, goggles for safety, gloves for safety, but in this case, sometimes a lab coat is more safe and sometimes it's less safe. This time, it will get all caught up, so no lab coat. All right, you ready to go?
I'm ready, let's do it.
Okay.
My goodness. 1.
Okay.
Because each of our electromagnets can hold more than my whole body weight, I can use them to cross the beam. When they're on, they stick like, well, magnets. And when I turn them off, they stop being magnets and I can move them along as I go. Now, this is something you should definitely not try at home.
Come on, Phil. You're almost there.
We did it! Yeah! There you go, Science Max, experiments at large, electromagnets!
You wanna go?
No.
You sure?
I'm positive.
Okay, I'm going again. Woohoo!
Crazy.
Oh, okay. Careful. Don't mess it up, Overwhelmo.
Overwhelmo.
Send in the next applicant for the Wizard Academy.
Overwhelmo. And now, I say the magic word. Overwhelmo.
I say the magic word. The magic word!
Well, that certainly does seem like magic, yep.
As I balance not 1 coin, not 2 coins. That's a 3.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Today's episode is about friction.
How can I hang on to this rope without falling?
Can we reduce it so we can slide around?
I'm going towards the wall!
Can we increase it so I can climb a wall?
Ha ha! I did it!
Can I use it to fly? Yep. Friction, today on Science Max Experiments at Large.
Hey, Science Maximites,
slippery. But that's okay, because today we're talking about friction. Friction is a force that is everywhere and happens when any one thing rubs against any other thing. We do lots of things to increase friction, like wear shoes with big treads on them. And we can do things to reduce friction, like the experiment we're doing today. We're gonna build a hover disc, and it's very easy. You take some cardboard and cut it into a circle, just like this. Then put a hole in the middle of the circle. You might want an adult to help you with that. And then take a plastic drink bottle cap, like this. I like to use the ones that you get on sport bottles because they have a little nozzle that pops open or closed. And then you glue it around the circle and you get this. Then you need a balloon. So you blow up your balloon. I know you know that step. And then twist the balloon so it doesn't get away from you. When it's nice and twisted, you can stick it over the drink bottle cap like this, and then untwist it. And this is why I like to use the plastic drink bottle caps that come from sport bottles, because you can open it when you want. And when you do, your disc rides on a cushion of air, reducing the friction with the table, and it's almost like it's sliding on ice. You can also use CDs if you want to do a different design. Just make sure you're using CDs you never want to listen to again. Now, if any of this is too fast, don't worry. You can always go to the Science Max website, where we have all of the instructions. And now, it's time to max it out. We're going to see if we can make a human-sized, rideable, low-friction hover disc. I'm going to the Ontario Science Centre, where hopefully I have an expert that can help me. Door is stuck. I think there's a little bit too much friction with it. Oh, that's got it.
Oh no, this isn't the Science Center. Did I go back in time again?
Oh. It is the Science Center. Helena, hi.
Hey, Phil. You're here to see the hover disc.
Yes, please.
All right, come on, right this way.
So I made one in the lab that works pretty great. It's on cardboard and it has a balloon. The one you have here works on the same principle?
Yeah, it does. But you know what? My friend Russell has some ideas about making something like this, but even bigger.
Do you think we can make one big enough to ride?
Maybe, yeah.
All right, well, let's take a look at the one you have here. Oh, I see. Right, this one works the same as the one I made. It's really hard to move the disc, but if you add some air, it floats like a dream.
There we go.
Great, so let's ride it.
Whoa, Phil, not this one, the one upstairs. You can ride that one.
Oh, okay.
Yeah.
Should we bring this one just in case?
No, it's a little heavy. I think we can leave it there.
What if we need it for reference?
No, I'm sure we'll be okay.
It is pretty heavy.
Yeah,
but...
come on. Let's go. Russell's waiting.
Are you sure we won't need it?
I'm positive.
Okay, but if we have to come back, I get to say I told you so.
Okay.
All right.
Hey, Ramona, you change your hair? Yeah, it's nice. It's like doing this now. Because but now it's, yeah, I like it. You should give me the name of your guy, because I wanted to, hey, oh, hey, how are you? You ever think to yourself, no matter what I do, I can't seem to get anywhere. I can't get enough traction? Well, you, my friend, need some more friction. Which one of these two shoes has more friction? Take a closer look. Huh? Right, bam. This one doesn't have a lot of treads. It doesn't have a lot of friction. But this one, it's got metal spikes on the bottom. This is called a cleat, and the spikes are for helping you grip onto the grass when you're playing soccer or golf, increasing its friction. Why do you think skis are smooth on the bottom? Come on, look at that. It's so smooth and glidey. My hand I can barely even touch the surface. It just slides right off. It's sort of glidey and smooth. They're smooth to help you glide across the snow, reducing their friction. Why doesn't this box slide down this ramp? Friction. This roller skate has wheels. Wheels reduce friction. But when I push the roller skate, how come it doesn't just keep rolling forever and ever and ever and ever? And going all the way around the world and writing a memoir. Say it with me. Friction. Louder. Friction. Can't hear you. Friction. Little too loud. Friction. Ease it back. Friction. How can I hang onto this rope without falling? Friction. How can I jump down on the floor without falling over? Friction. And now you know your friction. Your friction. Your friction. Come on. Uh-oh. Oh, Ramona, the friction sign is broken. Reset.
Uh-oh. The plan is to take our small hover disc and make one big enough to ride. So I'm off with Helena to another part of the Science Center to meet Russell, who has some ideas on how we can do it.
Oh, hey, Russell.
Hey, hi, Helena. Hey, Phil. How you doing, Russell?
How you doing, Phil?
So this is the hover disc.
This is our small hover disc, yes.
How does it work?
Well, obviously you sit on here,
right.
Air will go into here. It gets vented through all these separate holes here, so we get an airflow over the entire area. Hopefully this will work to pick someone up. All we need is...
Air.
Oh, well, that's easy, because the small one worked like this, so we just put the balloon on, right?
I hope you got the
Okay, so we put the balloon on the... hold on. Larger balloon!
Oh, okay.
Sorry.
That's okay.
Okay.
Yeah. Uh-oh, twist it so it doesn't...
He's losing his air.
Okay, all right. On you get.
You grab
Right.
one side, I'll grab the other.
Okay, here we go.
Go. It doesn't
feel way too much
It doesn't
friction
feel
on
like
it.
it still feels pretty frictiony. I think we might need something more than a balloon. So what do we do?
Well, I think we need more consistent air going through here.
Okay. So not a balloon.
Not a balloon. Something, I don't know, opposite to a vacuum cleaner?
Opposite to a vacuum cleaner. That would be
Like a leaf blower.
Like a leaf blower.
a leaf blower.
Right?
High fiving.
Yeah.
Awesome idea.
Yeah, leaf
so
blower it is.
why don't we make a couple larger discs when we'll hook some leaf blowers to them and we'll see what happens.
Definitely give it a go.
Okay, great. Carbon is an atom and is the basic building block of all life as we know it. You, me, all plants, all animals are carbon-based life forms. Other things are made of carbon too. Diamonds are carbon, coal is carbon, even pencil lead isn't lead, it's graphite, which is carbon. If you were to take all the carbon atoms in your body, you could fill 9,000 pencils. Of course, kind of prefer my carbon where it is.
Our low-friction hover disc still had way too much friction. One of the problems that Russell mentioned is that the balloon just wasn't giving enough air. But then Helena had the idea of using a leaf blower instead. The plan now is to make a leaf blower powered disc by starting with a big circle of wood, cutting a hole in the wood where the air will come through, and then covering the bottom with a tarp that has many holes cut out of it for the air to escape. Because leaf blowers are made to push lots of air, hopefully there'll be enough for me to ride it.
Well, this is the business. Look at
That's
this.
amazing.
It's good, right?
Oh, yeah, I love the tube. You know, high volume of air through that.
Yeah.
So yeah, I think it's a dryer vent I just found it in the lab. And then this, of course, is a leaf blower. So I get on here, and then Helena, if you want to turn it on.
Yeah.
So once we fire it up, the air coming out from the bottom of the disc raises me up, and I float on a cushion of air.
I can't control it!
Because the friction between the disc and the floor is so low, I end up floating wherever Helena and Russell push me.
I'm going towards the wall! It's like human air hockey! Okay. It's a bit unstable. Do you want to turn it off?
Wow, that worked amazing.
Not too much control, though.
I have no control whatsoever.
Yeah, no.
But this is great. So so we have the no friction down pat. I feel we need some way to actually move.
Well, something to push you along. I was thinking as you were going, like, you need like a broom or something.
A broom? Okay, yeah. What if we do like something low friction, like a broom, and something high friction, like that we could really sort of stick on the ground?
Yeah.
Yeah, and then we could build 2 of them, and we would have 2 discs and 2 ways of moving them.
Are we gonna race?
And we can race!
Yes.
Yeah! Okay,
Yeah.
race. That's what we're gonna do. Here is an experiment you can do at home with friction. This is a toy boat. Yes, you guessed that right. And this is a wooden plank. Correct, that's 2 for 2. I put the boat on the ramp and watch what happens. Nothing! The reason why is because the friction between the boat and the ramp is enough to counteract the force of gravity trying to pull it down. But watch what happens if I raise the ramp to the right height, the boat slides down because the friction isn't enough and gravity pulls it down. But when we change surfaces to this carpet, let's see what happens. Same angle, I can raise it higher, 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 because there's more friction between the carpet and the boat than there was between the wood and the boat. Now, if you're thinking that we're just gonna do it with a small ramp, you're wrong. Because of course we're gonna max it out. Hey, Helena.
Hey.
This is amazing.
Thanks, I made it myself.
Wow.
Ready to climb it?
Absolutely. Here we go.
Way to go.
Huh? Huh? No problem. So that was very easy.
Well, that's probably because the friction from your shoes is high enough so you don't slip.
Right, and the friction from my clothes is much lower, which is why I could slide down.
Right.
So how do we make it more difficult?
We'd probably have to make it higher.
All right, let's make it higher.
With the ramp at a steeper angle, I'll need more friction to climb up.
All right.
Ready?
I'm totally ready. Here I go. You try.
Okay, hold my turn. Here we go. Ooh.
Oh, so clearly we are not getting enough friction between our shoes and the ramp at this angle.
We should add some carpet, because carpet would add some more friction between our shoes and the ramp.
All right, let's add carpet. Sorry, here's your drill.
Thanks.
All right, carpet.
Yeah?
Same angle.
Yes.
And why have we done this?
More friction.
More friction. Let's give it a try.
Hey, way to go.
Totally able to climb the ramp. So, what do we do now to make it harder?
Make it higher.
Make it higher. Wow, it's really steep.
I don't think you're gonna make it.
Sure, if I take a really good run at it, I think I can do it.
I don't think so.
Well, there's one way to find out. No.
No.
Okay, so I can't do it. Is that it?
Well, how about Velcro?
Wow.
Right? It'll give you more friction, so you can try climbing with this. We'll give you Velcro knee pads, Velcro shoes.
Velcro. Velcro handholds, Velcro knee pad, Velcro on my shoes, helmet for safety, Velcro fill, Velcro dance. Okay, you ready?
Ready.
All right, here we go. Ha-ha, I did it! Creating friction between me and this ramp means I can stay up here for as long as I... No. No, Velcro. No. No.
Phil, you okay?
Velcro! Friction! Your turn.
No.
Our hover disc worked well. So well that we decided to build another. If we have 2 hover discs, then we can race them using different kinds of friction to push them along. Something that has low friction, like a dust mop, and something that has higher friction, like a pole with rubber balls at the end. Rubber has great friction. That's why we make car tires and the treads of our shoes out of rubber.
Okay, we have a giant race course that we've set up. We've got 2 low-friction hover discs, and I'm gonna use the low-friction dust mop version to propel my hover disc. And Helena, what do you have?
I have the high friction rubber ball stick.
start your engines! On your marks, get set, and go!
And we're off. Remember, Helena and I are using very different methods to get our hover discs moving. I'm using a low-friction dust mop, and Helena is using high-friction rubber balls. As you can see, my low-friction dust mop doesn't make enough friction with the ground for me to push myself. Helena, on the other hand, is having no problems.
Go, and go, and go, and go! Go ahead with the beat tip! He's way back! Forward! Bit further! He's way back for the win! It's the winner! Jake crosses the...
Yes!
And then we have our winner! Yes! Over the finish line. It feels way back over there.
I'm still stuck at the second turn. Way to go, Helena.
Thank
Nice.
you.
So what was the strategy? How did it work?
Well, pretty much while I was using those red balls, I was getting friction, helping me steer.
You know what? I think we need a little bit more thrust. That would work even better if we had something pushing us even harder.
Definitely.
Wait. I have an idea. Wait, hold. I need your help. Come on. I'm at iFly Toronto indoor skydiving to talk to you about friction. That's Mike. He's gonna help me out. Okay, here we go.
Unfortunately, we can't hear what Phil is saying because there's too much wind. It looks like he's trying to tell us something about the friction. Yes, he's saying the friction from the air rushing up in the chamber is enough to counteract the force of gravity, which is why he's able to float or swim or whatever he's doing. Now it looks like he might be saying even something like air can have a lot of friction if it's going fast enough. And the air in this chamber is going fast, which is why we can't hear a word he's saying. Oh, well, he seems to be having fun. So how important is friction? Well, let's say I'm out for a drive. Car tires need friction to grip onto the road. Without it, my car wouldn't be able to turn at all. But that's nothing. Without friction, the bolts holding the wheels on the car wouldn't work. In fact, none of the bolts, screws, or glue on the car would work, and nothing would stop moving or stick to anything else. Even the trees would blow away with the slightest breeze. Friction is everywhere, and without it, nothing would work.
Okay, hover disc race round 2. This time we decided to have a little bit more thrust, so Helen and I are going to be using fire extinguishers. Now, do not use fire extinguishers at home. Fire extinguishers have a very important purpose, and it's not for this, but we've got these ones special. Are you ready, Helena?
Oh, yeah.
Oh, yeah. Okay, here we go. Russell?
So, racers, start your engines. And go!
Using fire extinguishers gives us a lot of thrust. But because the discs we're riding on don't have any friction, wherever we point ourselves, we just keep going in that direction, which makes steering very difficult. Cars grip onto the road and can go around corners thanks to the friction of their wheels. When you have no friction, it's kind of like moving on an ice rink.
Oh no! I'm out! Yeah! High five! Yeah! High five! Yeah! Okay, wait.
Oh, I ran out of fire extinguisher at the end there, so I had to cheat a little bit. So 1 for you, 1 for me, and all of them for friction.
Or the lack of friction.
Or the lack of friction. Science Max, experiments at large. What do we do next? Larger fire extinguishers?
I think so.
Oh,
Okay.
yeah.
See you next time. I know where we can get some, actually. We can go, if we go to the fire extinguisher store where we got these fire extinguishers, we can get like a rack of extinguishers.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Carbon is an atom that is the basic building block of all life as we know it. You, me, I hit myself in the head with the friction sign. That's more of an impact, not friction, really. How can you destroy my life anymore? Set, huh?
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about elastic energy. We use it to build a catapult and a paddle wheel boat, and then we max them out. We even learned some history. Elastic energy. Today on Science Max, Experiments at Large.
Welcome to Science Max Experiments at Large. I'm Phil McCordick, and today we're going to be building one of the most devastating, one of the most powerful machines known to medieval man, using a plastic spoon, among other things. We're going to be building a catapult. Catapults were used throughout history for all kinds of reasons, to throw all kinds of things, but mostly big stone blocks at castle walls in order to knock them down. Here's what you need in order to build your own catapult. You need elastics, pencils, unsharpened is fine, plastic spoons, like I said, and popsicle sticks. Popsicle sticks. Popsicle sticks. I'm gonna go wash my hand. So, here's the science behind what we're doing today. It's all about elastic force. Elasticity is a property of solid materials, like this elastic, and how much they tend to return to their original shape when deformed, like when I pull on it. Elastics are called elastics because they're great at doing just that. You can pull on it and pull on it and pull on it, and it'll, always return to its original shape. So we are using the power of elastic force today. Ow.
Now it's time for a Science Max quiz. Elasticity is the ability for a material to return to its original shape when deformed, like this or this. Which of these materials have elasticity? A rubber band, a pencil, or a rock? Haha! This is a trick question. The answer is all three. Most solid materials have elasticity. Nearly everything will deform a little and still be able to return to its original shape. It all depends on how much. This is a steel bar. This is an elastic band. And this is an ice cream sundae. We're not talking about ice cream sundaes now, though. So get that out of here. Good. Now, a steel bar and an elastic band both have elasticity. A steel bar can be stretched to 1% of its length and still spring back. A rubber band can be stretched 300% or more. The difference between the two is why we make balls out of rubber and buildings out of steel, because the other way around wouldn't be good for balls or buildings. This has been a Science Max quiz.
All right, let's build our catapult. The first step, take 4 pencils and stick your popsicle stick in between so you have 2 on the top and 2 on the bottom. And then use your elastic to go around and around and around. That's why I like building things with elastics, because it makes it very fast to tie things together, because once you go around and you have it nice and tight, you just pop it over the end and voila, it stays together. And that is how you start making your frame. Put more pencils on that side.
And another popsicle stick on the other end, held on at the corners with more elastics. Then take even more elastics and put them right around the middle until you get this.
I've added a few more elastics around the middle here, and that is where we're gonna get all of our elastic force. I think I have 6. The more you use, the better it's going to work. Take your popsicle stick, stick in between the elastics, and then start spinning it around. Here's the reason I use pencils and popsicle sticks, is because the pencils are a little bit longer, which allows you to twist the popsicle stick around in the middle and build up the elastic force. Now, because I'm twisting, the elastic force we're using here is called torsion, or twisting force. When you feel you have enough torsion, pull your popsicle stick down a little bit so it won't unwind on you, and you'll see that you have all kinds of elastic energy. Then, take your spoon and stick it on the popsicle stick, and you can also break off the popsicle stick if you want to make sure it's the right length. And it works like that.
To make the frame, you just need more pencils and elastics. The trick is to make a triangle with 2 pencils attached to your frame. They should stick up right where your catapult arm would be fully upright. Then, take a final pencil and put it across the top. Don't forget to pull the arm back before you put the pencil across, otherwise it'll end up on the wrong side.
Now, this is very complicated, and I went pretty fast, so if you want the step-by-step instructions on exactly how to build this, go to our website. And there you go, a catapult of your very own that you can use to knock down very small castle walls. I've also built a larger catapult using all of the same principles. Pretty good, huh? It's got a longer arm, which means I can throw marshmallows even further. Whoa. Or I can throw larger marshmallows, or I can throw very large marshmallows. Now, I know what you're thinking. You're thinking, Phil, is that the largest catapult you're gonna make? Well, of course not. This is Science Max, experiments at large. I'm headed to the Center for Skills Development and Training, and we're gonna max out the catapult so that it's big enough to throw one of these. Hey, Zach.
Hey, Phil.
How you doing?
All right.
This is Zach. He's a mechanical engineer, and you build machines for a living, right?
That's right.
Great, because I need help building a catapult.
Okay, but what's with the pumpkin?
Well, the pumpkin is what I want to throw out of the catapult. See, I figure we just take the small design and we just make it so that we can throw one of these. What do you think?
You're gonna need a really big catapult.
Yeah, and I'm also gonna need some really big elastics. Where do you get those?
Well, in medieval times, they used rope to make large catapults.
Oh, okay, well, rope is a lot easier to get, and that would be fine. And I want to make this arm as long as this piece of wood here.
This is gonna be a huge catapult.
It's a huge catapult. I guess we should build it outside, though, huh?
Let's do it.
Okay, it's over that way.
Okay.
I'll follow you.
Sure, do you want a hand with that?
No, I'm fine. You go ahead, and
Okay.
I'll just, maybe if you hold the door open for me, I could just hold, no, you know what, you go and I'll meet you.
You sure you're good?
Our full-size catapult is going to look a lot like the popsicle stick version. We start with a 4-sided frame and add some legs on the bottom. Our spoon is going to be replaced by a long throwing arm with a basket on the end. Then we need a really strong cross brace at the top to stop the arm. Just like in the small version, using a triangle shape is the best because triangles are very strong. Finally, we need something to wind around and around, which is going to give us our elastic force. Instead of elastics, we're going to be using rope for our catapult because rope has just the right amount of elasticity. But unlike medieval times, we're going to be catapulting pumpkins. Once Zach and I got it all put together, it looked like this.
Okay, we have built a catapult. Check it out. It's pretty solid, and I think it's pretty amazing. And just like in the small catapult, we have our elastic force. But this time we're using rope, right, Zach?
Yes.
Okay, and rope will work as well as the elastic did in the small one?
Yeah.
All right, great. So what do we do? It's really loose now.
We need to wind this up so that we put some tension into it.
Go!
The reason a catapult works is because the rope is twisted. The elasticity in the rope wants to unwind, which gives the catapult its power. Just like the small catapult, the more you wind it, the better it works.
Good. Usually in medieval days, they had whole teams of people doing this job, but it's just me and Zach now. How you doing, Zach?
All right.
Okay. And then we clamp it on here. So the thing doesn't unwind, right?
Yeah.
Good. All right, now we have our pumpkin, and we're gonna fire our pumpkin in our castle wall, which is made out of cardboard boxes over there. Pumpkin. All right, here we go. Pull on the arm back. Oh, that elastic force is pretty strong. Okay. How do you think you think that pumpkin's a good size?
Oh, it's pretty big.
You think?
Oh, a little too big.
It's too big for our basket.
Yeah.
Smaller pumpkin! Smaller pumpkin! I'll hold this. No rush, Zach. No rush. Okay, rush, Zach. Can't hold.
Oh, yeah.
Can't hold arm. Okay, ready? 1, 2, 3! It didn't work that well.
No, not quite that well.
Yeah, so it went, and it flew, and it landed here, which is a little farther away from the wall than I'd like it to be. 1/3 of the way to the wall! I don't know if that's enough. What do we do to make it better?
Well, the way we're throwing it right now, we just have the pumpkin in a, at the end of the arm. But if we make some kind of a sling so that we fling it as we're bringing it up.
We make a sling?
Yes.
All right, I don't know how to make a sling, but you know how?
Sure.
All right, we'll make it, and then you can explain how it works.
Yeah.
All right, good. Let's put the pumpkin over here. We'll recycle it later.
Max Historica.
Good morrow to you. I am Lord Fillington III, and welcome to my medieval castle. Throughout history, lords and kings have built castles and walls to keep people out. I built my castle to protect my prize collection of snow globes. I have so very many, and they're all mine. Ha ha! Oh, hello! You down there! You can't come in. This is my castle.
And throughout history, there have been people who've been wanting to get into those castles because Lord Fillington has been hogging all the snow globes, and I'd like to look at them. But the hard part is figuring out how to get into the castle, because I can't just come up to the wall and start hammering on it. Huh?
Taste the wrath of my water balloon!
Because if I get too close to the castle, he can get me.
Ha 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 ha! Fortunately, there's this thing called a catapult.
Oh, fiddlesticks. They have a catapult.
What you do is you put something heavy in the end here, and the catapult fires it at the walls of the castle, knocks them down, all from far enough away that the people in the castle can't get to you. Ah! Oh, I surrender! Don't knock my walls down! It'll take me all week to fix them. Oh. All right, you can have a snow globe. Oh. And that's how catapults were used in history. Oh, so beautiful.
Back to our maxed out catapult. Our first design threw a pumpkin just like it was supposed to, except it only threw it 1/3 of the way to the wall. Now Zach and I are planning to outfit the catapult with a sling. The sling attaches to the end of the throwing arm and gives the pumpkin a lot more distance to travel. Because the pumpkin is traveling a longer distance in the same amount of time, it will be going faster, which will hopefully get it to the wall, or at least a lot farther than before.
So we built this sling. How does this work, Zach?
Well, we've got one end tied here.
Yeah.
And then we put the pumpkin in here.
Wait. Okay, pulling arm down. Pulling arm down. Okay, yeah, now what?
Now we put the pumpkin in here.
Put the pumpkin in there.
Yeah. And then we loop this over the back of the... Over that. As the throwing arm goes up, this will slide off the back of the throwing arm and it will release the pumpkin.
All right, you're the expert. I believe you. Let's try it out. 3, 2, 1. Whoa! Okay. That works really well. You know what the problem is, though? We still don't have enough oomph.
Yeah, it needs more power.
So what do we do? I don't know if we can crank that rope anymore.
I think we're at the limit of our rope power, but if we added some more elastic...
I thought we weren't going to use elastic.
Well, we used elastics in our small demo model, so what if we use some more?
We have elastics? I don't know
Yeah,
if
I brought some in here just in case.
What's this?
It's surgical tubing.
It's like a giant elastic. Well, I guess this is elastic force, so do we twist it around at the bottom there?
Well, we just wrap it around the throwing arm like this.
Oh, I see. So we tie it here.
Yeah, we just need a lot more, and then...
And then we pull this, and it would be... Oh, yeah, that would make a lot more. So we just need a lot more of this elastic... What is this again?
Surgical tubing.
Surgical tubing. It's like a giant elastic. Fantastic. All right.
Goggles on.
Goggles on. Yes. Yes.
Here's another fun way you can play with elastic force. Take a milk carton. I prefer Science Max milk because it's the creamiest. 2% cream, 100% science. Wrap some elastic bands around it with some popsicle sticks on the bottom, sort of like feet. Then take some clamshell packaging, which wraps just about anything you buy nowadays, and cut out a square or a rectangle. Then wrap some tape around that square with an elastic in it, and put the elastic on the feet of your milk carton. Then wind it around and make sure you go backwards so your paddle wheel boat will go forwards when you put it in the water. And there you go, a paddle wheel boat. Now it is time to max it up. Ahoy, the SS maxed out elastic force paddle wheel boat mattress. I need a better name. But I've made a giant paddle wheel boat that will work on elastic force because I've got surgical tubing as my elastics, and that's an air mattress. And then I use some lumber to hold it all together. And of course I need a paddle wheel, and what better thing to use in a pool than a flutterboard. Okay, here we go. So normally you're not allowed to wear your clothes and your shoes in the pool, but I got special permission because of science. Besides, I'm not worried at all, so I didn't wear my swimming outfit because I figure I can totally do this entire experiment without even getting wet. That is how confident I am. All right, now the tricky part, we'll be getting onto the mattress. Okay, here we go. Ha-ha! Whoa. Ha-ha! The SS Science! Hey, SS Science, that's a great name for this. Look, it works great, and I managed to stay totally dry. Huh? Well, almost. Whoa, oh. Haha, you thought I was gonna fall in the pool, but I didn't. Uh-oh. My flutterboard has stopped moving, and I'm in the middle of the pool. Almost. Yeah. Didn't think this through. No. 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 No, that's not going to work. Maybe I'll wait. Our maxed out catapult was working well with the sling we attached to it, but it still didn't make it all the way to the wall. Zach's idea is to attach a bunch of surgical tubing to the cross piece of the catapult. Surgical tubing is pretty much big elastics, so we'll have two places we're getting elastic force from, the rope and the surgical tubing. Hopefully this design is enough to help our catapult fling a pumpkin far enough to hit the castle wall. All right, here we go. You hold that. I get this.
we got our system down now. Okay. Oh. This goes up to there. Okay. Okay. 3, 2, 1. Nope. One, 2, 3. Oh! It went too far. It went too far. That's so good. Oh man. Right. Okay, so all we gotta do is move the catapult back. So you get that side, I'll get this side, and we'll move the catapult. See, now our catapult is too good. We gotta back it away from the castle. All right, let's go again. Aha, pumpkin.
Pumpkin.
Pulling arm back.
Pulling arm back. Grunting.
Loading. Pumpkin. Hooking rope on arm.
Hooking rope on arm. More grunting.
More grunting. Pulling back strongly. 1, 2, 3. Oh. Oh. Oh, wow. Woo.
We're inside the castle.
We're still inside the castle. Oh, man. It's an excellent shot, though. So what do we do? Move the catapult back?
Yeah.
Move the catapult back. What about
here?
Here. Here we go again. Pumpkin.
Pumpkin.
Loading arm.
Loading arm.
All right, you ready? You think it's gonna work? We've done every modification we can possibly do. So you think it's gonna work this time?
We did it. It's gonna work.
Okay, here we go. I'm excited. All right, ready?
Ready.
1, 2, 3. Whoa! Yeah! Woohoo! High fives! Well, there you have it. Awesome job. Now we need to throw fingers to see who gets to rebuild the castle. Okay? 1, 2, 3. Oh, thanks very much for joining us. Let's take a break. I'll rebuild the castle. You see, this is exactly how catapults used to work. They'd hit the same part of the wall over and over until they made a big hole, and that would weaken the wall. Fortunately for me, it's really easy to fix. Just put this right in here. Oh, man. The pool will be closing in 5 minutes.
No, I'll do it. No, why do you want to?
Taste the wrath of my water balloon! I don't believe it really sells it if he doesn't smash the water balloon. Does he? Good moral to you! I got my feather in my face. Oh, you gotta be kidding me!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about vibration and frequency. Frequency and vibration. What's the difference? We build a maxed out vibrobot, spin a giant disc, suspend water, and play with lasers. All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites, and welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max Experiments at Large, we're going to be looking at vibration. Vibration is when things go back and forth, and back and forth. All kinds of things vibrate, like pendulums. Pendulums. Wait, and pendulum. Pendulums are designed to swing back and forth. Stop that. Also, metronomes. Metronomes are used by people when they're practicing music to keep accurate time. Yeah. Okay, putting it back. And, okay. We're gonna be building. Whoa, okay. We're gonna be building. This little guy. This is a Vibrobot. And he vibrates and he skitters around on the paper. And if we take the caps off the markers, he makes interesting patterns on the paper. Okay, so let's get started. Let's build a Vibrobot. Okay. Oh yeah, you know what? Maybe it's time to take off the ski boots, huh? Whew. There we go, that's better. So today, like I said, we're gonna be making a Vibrobot. And here are all the materials you need to make your own. Plastic cup, 3 markers, an electric motor, just make sure you ask an adult first, a battery, a plastic drink bottle cap, a toothpick, scissors, this kind of tape is called electrical tape, science tape, which is the same as invisible tape, but of course I use this tape only for science, and some modeling clay. And these are 2 bendy straws that I've taped googly eyes to. These are not necessary, I just like them for decoration. Now remember, if I'm going too fast here, which I probably will be, you can get all of the steps on how to make your very own Vibrobot on our website. Okay, so here's how you get started. First, you're gonna make the feet for your Vibrobot. So I attach some science tape to the markers, and then I put the marker on the bottom of the cup. And then I do that again to the next marker, and then the third, balance it like that. There. Next thing you wanna do is take your plastic drink bottle cap and make a hole with a toothpick. You wanna make it off to the side, right about there. Just like that. That's so when it turns, it will be off center. That's what's gonna give us our vibration. So once you've made that hole, take some modeling clay and stick it in the cap to give it some weight. When you've done that, stick it onto the shaft of your motor like this. See how it's off center there? Now we just need to attach it to the Vibrobot. I just put it right here on the top, and I like to attach the battery to the back of the cup. And now, finally, we're going to attach the eyes. We take some science tape, and we put the straws over here. I am Vibrobot. I am here to vibrate. Take me to your leader. So then, you attach your tape with the wire to the top of the battery there, and then the other wire to the bottom of the battery, just like that, and let your Vibrobot make some art. Ha 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 ha. Now, if the battery is new, your Vibrobot might be jumping up and down quite a bit. So you can do what I like to do and add some more weight, and then you make better lines with your Vibrobot. And your Vibrobot makes art. How long will he last? Probably till lunch. And there you go, Vibrobot art. Art made by a robot. How cool is that? So that's what we're gonna do today. I'm gonna meet Chris from Logix Academy, and he's gonna help me max out the Vibrobot. Plus, we're gonna learn a little bit more about vibration. Come on. Oh, hey, Chris.
Oh, hey, Phil.
Thanks for coming.
My pleasure.
Okay, here's your Science Max lab coat.
Thank you.
So you guys at Logix Academy, you also build a Vibrobot, right?
That's right, we do.
This is mine, and it works pretty well.
That's awesome.
So, I want to max this out.
Cool.
So I thought we would start with, instead of this motor, we would start with this motor.
Wow.
It used to be a round circle, but I cut it off so that it's off center.
Perfect.
I've also got, this is our battery.
Fantastic.
That's as far as I've gotten so far.
Well, it looks like we need a frame next.
Right, something to be the cup.
That's right.
So we just need some sort of larger cup.
Ooh, how about that metal shelf over there?
Oh, this thing?
Yeah.
This is just something I keep my parts on.
It's perfect.
Really?
Yep, the shelves will house everything that we need, and it looks like it'll be strong enough to hold everything together.
Now, the Vibrobot had markers on the bottom of it.
That's right.
To make a little pattern. Should we try that with this?
Because we're going bigger, what if we use paint and paintbrushes instead?
Okay, sure. We could attach paintbrushes to the legs. Pass me one. All right, so now all we need to do is get some paint and some paper.
That's right.
And we can fire it up. Okay, let's move it over this way.
Vibration and frequency. What's the difference? They're all connected. Ta-da! Now, whoa. Vibration is things going back and forth. Back and forth. And back and forth. It's a cycle. Cycle, 25 bucks. Oh yeah, it's the wrong kind of cycle. Never mind. Well, if that's vibration, then what's frequency? Well, frequency is a measure of how fast or slow, how frequent those vibrations happen. Look at this bowling ball. Look. It is swinging back and forth, but not very fast. You could say it has a low frequency. We measure all kinds of things by their frequency. This thing is terrifying. When you turn the dial on your radio, you're tuning in to different frequencies of radio waves. Hey, look at this punching balloon. It's going very fast. You could say it has a high frequency. So, now you know. Vibration is something going back and forth, and frequency is how quickly it does it. Ramona, the bowling ball keeps coming through everything. How do you turn it off?
Okay, back to our main experiment. Chris and I are taking a Vibrobot and maxing it out. We have a large motor and a battery, and we're taping it all to some shelving. Just like our small Vibrobot, our motor needs something to make it unbalanced when it spins. That's what will cause the vibrations.
It's just taped. I haven't attached it in any other way. Do you think that's okay?
As an engineer, I have superior faith in duct tape.
Okay, well, that's good to know.
We're also adding an on-off switch and some paintbrushes on the bottoms of the legs so our maxed out Vibrobot can make art just like the small one. The final step, dipping the brushes in paint and setting it on a big piece of paper. We fire it up and it immediately shakes everything off the shelves.
Oh! It totally spilled all the stuff on the shelves.
The motor shakes the Vibrobot a lot. But there's a problem. All that shaking is starting to take its toll on the shelves. The wheels come off, the screws come out, and finally...
Whoa. It totally shook itself apart.
Destroyed itself.
The shelving unit just completely falls apart when it's being shaken.
Vibration is really hard on the structure of an object. We need something more sturdy, something that can take weight.
Steps, maybe?
Yeah.
Okay, hold on.
Okay.
Okay.
Yeah, this looks much better.
Okay, great. So we build the new Vibrobot out of this. So more paintbrushes.
Bigger motor, more paint.
More everything.
More everything.
All right, good. This is a pendulum. It's just a weight suspended on a line and anchored from above. Pretty simple. Pendulums were used for hundreds of years for all kinds of reasons, but most famously in clocks. Why were pendulums used in clocks? Well, here's why. Let's mark every time the pendulum hits the bottom of the swing, right here. Okay, watch. All right, now here's the question. How fast will the beeps be if I swing it from much higher up? Let's find out.
No matter how high the pendulum swings, it keeps the same frequency. That's why they were used in clocks, because it could swing for a long while, and even though it would lose energy, it would still keep perfect time. The frequency of a pendulum doesn't change, no matter how high it swings or how much weight is on the bottom. The frequency comes from how long the line is.
Now this is a pendulum wave.
Because each bowling ball has a line that's a different length, they have a slightly different frequency. They start out swinging together, but soon they start to make interesting patterns. Remember, each pendulum is keeping its own perfect time, even if it's slowing down. It's only the length of the line that gives each pendulum a different frequency.
And now we're gonna max it out with well, I guess these are already bowling balls, so this is already pretty maxed out. I'm just gonna leave that there. These are balloons. This is a laser, and these are awesome laser safety glasses. Now, lasers are made of light, And light has a frequency. In fact, each color of light has a different frequency. This is a red laser. Check it out. Yeah, cool. This is also a very powerful laser. Oh, I can pop the blue balloon with the red laser because the blue absorbed the red light from the laser and then it heated up and the balloon popped. But here's the cool thing. I cannot pop a red balloon with a red laser because the red balloon reflects the red light from the red laser and I can't pop it. If I wanted to pop a balloon with a red laser, I need to use a darker balloon, one that absorbs the red light, like a black balloon. So there you go. Lasers, frequencies of light. I'm gonna keep this red balloon because it's always nice to have a balloon.
Chris and I are maxing out the Vibrobot, but our last version shook itself apart. Now the plan is to start with something more solid and try again. We found some very solid steps and added an even bigger motor, an even bigger battery, and attached a half-circle wheel to make the vibrations when the motor spins. We add some paintbrushes and fire it up.
Here we go! Come on!
Go, Vibrobot!
It wants to move.
Is it moving at all? So it's still not working. It's sort of getting caught in the paper and it's on the paintbrushes.
And the paintbrushes seem to be absorbing too much vibration and then the paper's stopping it as well.
So why don't we remove the paintbrushes?
Yeah.
And we might as well remove the paper if we don't have any more paintbrushes.
Yes.
And we'll see what happens.
We'll see what happens.
Okay. No paintbrushes, no paper.
Okay.
Now let's try it. 3, 2, 1, go!
Yeah! Aha! It's moving. Not bad.
The shaking is good, but I don't know if the shaking is enough. So what do we do?
Well, we could add another battery.
Another battery which would give it more power?
That's right.
Okay, let's try that.
Okay.
Okay, so it wasn't working before.
No.
Not enough power. And now we've got a second battery here.
That's right. We've wired them up so that one power feeds into the other, so we've got twice as much juice as we did.
So it's just a matter of clipping this onto there.
That's right, but hold on.
Yeah, safety glasses, because now we don't know what's going to happen anymore. Ready? 3, 2, 1.
The extra battery makes a big difference. The new Vibrobot shakes around and only shakes itself apart a little.
All right, that was amazing. Okay, so all we needed was more power.
That's right. I think it didn't have enough power to vibrate up and down, and that's why it wasn't moving every time it hit the ground.
So I think if we're gonna use this much power, I think we need to build it again.
Okay.
Build it even stronger and with a bigger motor.
Yeah?
And more power. And then maybe I ride it. You think we can build that?
Of course.
Of course. Okay, let's do it. You want to see something cool? I can make this water levitate, defy gravity using the power of science. You want to see? Behold! Gravity-defying water! I can even make the water go very slowly. Or I can make the water go back up into the hose. Or I can make the water completely stop. You know what's interesting? The water does not seem to be stopped for me. You see stopped water because you are looking at it through a TV camera. See? Real life, TV camera. Real life, TV camera. You see, movie cameras and TV cameras take a whole bunch of still photos and then run them together really, really fast. 24 times a second for our TV cameras. I have created a device that drops water at 24 times a second, and what happens is everything lines up. So it looks like the water drops aren't moving. But watch this. I grab the hose and it's fine. But I let it go, and the hose is vibrating back and forth at exactly the same time the camera shutter is going back and forth, and everything looks like it stopped. The power of frequency has defied gravity. Okay, so not really. It's kind of a camera trick. but I prefer to call it science! Here's a fun way to play with things going back and forth. This is Euler's disc, and it's designed to spin like this. What's going on is friction and gravity are slowing that down and pulling it towards the Earth. Now, you don't need a fancy disc like this to do this at home. All you need is a pot lid. Check it out.
When the pot lid spins, friction and gravity start to slow it down, which means each spin gets lower and lower, and the frequency gets higher and higher. But the difference between a pot lid and Euler's disc is Euler's disc is made to go for as long as possible. The heavy puck has a slightly rounded edge and sits on a glass surface that is slightly concave, like a bowl. All of this is designed to make Euler's disc last a really long time, which is quite a while. But eventually, friction and gravity pull the disc down, and finally, it stops.
Pretty amazing, right? Well, wait till we max it out. This is Trevor, head of the Science Max build team.
Hey.
Thanks for setting this up, Trevor. So what is this?
This is a giant side of a spool, big hydro spool.
Okay, so this is the largest disc that we could totally find, and we've got it all hooked up here. We lift it up, we spin it, and then you pull the thing and it will drop down and spin like a coin, because it's the only way we can do that with something this heavy.
Yeah.
Ready?
I'm ready.
Okay.
Trevor and I hoist it up and get it suspended above the ground. Then I start to wind it up.
Ready?
When it's going fast enough,
And go, Trevor!
Trevor pulls the release and it turns out a 200-kilogram spinning disc works exactly the same. As it spins and rolls, gravity and friction work on it, and the frequency speeds up as it gets closer to the ground until it stops.
Giant Euler's disc. Nicely done, Trevor.
That was awesome.
That was great. Let's do it again.
All right.
Our Vibrobot was working well, so that means it's time to make it way bigger. We started with a big metal table and added a huge motor, one 20 times as powerful as the last one. Instead of batteries giving us 12 volts of power, we're going to use a plug, which is 10 times more power. We've added an off-center wheel for vibration, bolted the motor to the frame, and added a protective cage all around to prevent anything from flying off. It even has a seat for me to ride.
Okay.
Okay.
You ready?
Ready?
Here we go.
We fire it up and it's very shaky.
Oh, wow. Wow. That was really uncomfortable. It was like very bangy, even with the seat.
Yeah?
I'm gonna try standing on it.
All right.
When I try standing on it, the Vibrobot lives up to its name. It vibrates all around the lab.
Oh, wow. My legs are numb to the knee.
I'm not surprised.
Vibrobot!
All right.
Yeah, that worked really well.
That was awesome.
I really can't feel my feet right now. And it held together, which is impressive.
That's right. The more power and the stronger structure paid off.
Yeah. The only thing I regret is not getting a chance to... Wait a minute, come with me! Okay, so I achieved my dream of riding the Vibrobot.
You did.
But we never got a chance to make art, so we've dipped a whole bunch of nuts and bolts and heavy things in paint.
Yep.
And now we're gonna turn on the Vibrobot and see if we can make some art. Let's see how it looks.
Oh, wow.
Ta-da! Vibrobot art. Vibrobot has been a huge success, and we got some art to keep. High fives. Well done. Science Max, experiments at large. Who gets to keep the art?
Rock, paper, scissors.
Okay. 1, 2, 3. Okay, tie. 1, 2, 3. Tie. 1, 2, 3. 1, 2, 3. Wow. 1, 2, 3. Ah, tie. 1, 2, 3. Man, There's going to be a red balloon, but those red balloons are going to be pushing this way. And then this afternoon, we're going to have this blue balloon, which is quite nice. Over to you, Kathy. Thanks, Kathy. Science! I figured we would have maybe a bigger motor.
Yes.
Or a bigger, no. I'm going to try that again. All thrusters ahead. Whoa! Balloons. Science.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Today, we're moving air. We're moving it through a tube to make a stomp rocket, vacuuming it out, turning it into a vortex, and taking it with us underwater. All on this episode of Science Max, Experiments at Large.
That was amazing! Greetings, Science Maximites. My name is Phil, and it's moving day today on Science Max Experiments at Large. Let's see, where do I put this? This is probably a good spot. Today, we are moving air. You probably don't think that moving air will have a huge effect, but you'd be surprised what you can do by just moving air. But don't worry, we're not just gonna move the air around in boxes. We are going to build a rocket! And this rocket uses the science of stomping on something with your foot. This is a stomp rocket, and it works by stomping on this plastic bottle, and air shoots through this tube and pushes the rocket up into the sky. And here is how you can build one of your very own. And remember, if I go too fast, don't worry. All of the steps are on the website, so you can follow along at your own speed. All you need is a 2-liter plastic bottle, 3 kinds of tape: electrical tape, duct tape, and science tape. Science tape is just the same as invisible tape, but I use this kind of tape for science. Then you want some plumber's tubing and some construction paper to make your actual rocket. First, you want to take your plumber's tubing and cut it into 3 lengths. And when I say you, I mean an adult, because you need to use a saw. So you saw it up into a long piece, a short piece, and an elbow piece. We want to make a long tube at the top, and then we also want to make a tube at the bottom so we can attach our 2-liter bottle to. And there we go. Ta-da! Ready to go. But of course, it doesn't stay up, so we have to attach it to a base. And it will look like this. And you see, it's been attached with duct tape here, and I've used electrical tape, and I've wrapped that part around there. Now, building the rocket.
Wrap the paper around the tube and tape it with your science tape. Tape the top closed so no air escapes. Then cut a semicircle to make the nose cone, and 3 hoops for thrusters, and tape them to the bottom.
There you go. The rocket fits on the tube just like that. And when you stomp on this bottle, it launches. But here's the most important part. The one most important rule of launching rockets. You shoot rockets outside. Come on. Once you get outside to a nice open area, and you bring your safety glasses with you, all you need to do to make the stomp rocket work is, of course, stomp on it. You ready? Here we go. 3, 2, 1. Whoa! You see that? That was amazing. Okay, so this is where we're gonna start with the stomp rocket. I'm gonna meet Chris from Logix Academy, and he's gonna help me max it out. In fact, he's probably at Science Max headquarters already. I should get over there. Okay, where's the... Oh, there it is. Okay.
How you doing?
It's good to see you.
You too.
Chris is from Logix Academy, and you guys do in-class robotics workshops, right?
That's right, we do.
Great. Well, I was hoping I could get your expertise to help me max out the stomp rocket.
Yeah, Logix makes one of these. I totally think I can help you with that.
Fantastic. So it works great. I just want to make it bigger, better, more maxed out.
First off, we can start by making this pipe a little bit bigger. So larger pipe, more airflow, bigger launch.
Okay, let's do it. Cool. Moving air isn't that hard, right? I mean, air is super light. How hard can it be to move? Well, here's an experiment you can do that lets you measure how hard it is to move air. So what I'm gonna do is I'm gonna hit the ruler with the broom. It's gonna go over there. I hit it, and it moved, no problem. So we're gonna do it again, except I'm gonna add just a couple pieces of newspaper. All right, ready? Aha, the ruler broke because this time I wasn't just moving the ruler, I wasn't just moving the ruler and the newspaper, I had to move the ruler, the newspaper, and all of the air that was on top of the newspaper. And that resistance was enough to break the ruler. Pretty good experiment, right? Let's max it out. I've got more table space, I've got a piece of lumber, and instead of a newspaper, I have a tarp. Now the tarp is very light. It is not the weight of the tarp that is going to be the difference. It is how much air I need to move when I hit this piece of lumber. And I've got a Science Max hammer. So first of all, you're not gonna try this at home, right? Deal? Okay, deal. No trying this at home. Okay, here we go. Moving air, test 2.0. It broke, and it didn't even move. Did you see that? I wonder if we can max this out even more. 2x4, which is much bigger than the piece of wood we used last time, and a sledgehammer. Here we go, moving air experiment 3.0. Yeah, science. Whoa. So I've joined Chris from Logix Academy, and we are maxing out our Stomp rocket. To do that, we're gonna use
Larger pipe, more airflow, bigger launch.
The theory is that moving a larger volume of air through wider pipes will make our rocket work even better. So we get to work. This version is built exactly the same. We cut and attach the pipes, a long piece, an elbow, and a short piece, then secure them all down. We attach the plastic water bottle and tape it so it's airtight. And then the only thing to do is make a new rocket that fits over the larger pipe.
Ready to try it?
I'm ready to try it.
All right, let's do it.
Let's go.
1, 2, 3, go! That was amazing!
In the end, though it worked, it wasn't much better than the smaller rocket.
I think we could still do better, right?
Oh, yeah.
This is Science Max, not Science Medium. Right, okay, let's go back to Science Max headquarters. Vacuum sealing. That's what you call it when you take all of the air out of something, often a bag, to seal in the freshness of food. I will demonstrate using this Science Max banana. 100% banana, but with added science.
Not all bananas contain science.
Here's how you can do it at home. Put your food in a bag, seal it most of the way, because we have to take out the air from the bag. And we will do that with a straw. Put a straw inside the bag, and then suck the air out of the bag, and then seal it at the very last second. There, a vacuum sealed banana. Now I know it's kind of hard to see that it's been vacuum sealed because bananas don't really crush much when you take the air out. So I like to use stuff that has a lot of air in it to begin with. In fact, there are special bags that are specifically for vacuum sealing that are supposed to store big and bulky items that have a lot of air in them, like this pillow. See this nozzle right here? It's designed to be used with a vacuum. Haha. So, what you do is you put the vacuum on this nozzle, open it up, and then you turn the vacuum on.
Oh. The vacuum is sucking all the air out of the bag, just like we did with the banana. But because the pillow is full of air as well, it starts to shrink and shrink.
Then you pull off the vacuum and you tie the seal off. And, all right. And ta-da! A vacuum sealed pillow. Okay, let's max it out. What could possibly be more maxed out than a vacuum sealed pillow? Vacuum sealed fill. Okay, I put plastic bags against the door and then sealed the edges with duct tape. And of course, I didn't put any plastic over my head because you never put your head in a plastic bag, right? Well, let's see if vacuum sealed fill, it works. Whoa. Hey, it's working! Ha-ha! The vacuum sucks all the air from the bag, which seals the bag and me in it to the wall. That means I should be able to knock this milk crate out from under me. Air pressure, or the lack of air pressure, is keeping me sealed to the door. I'm completely suspended! Uh-oh. I shouldn't have done that. No. So our larger version of the Stomp rocket worked, but it didn't go as high as the first version. Chris and I see how we can improve the design. The larger pipe and the larger rocket works really well.
It does work really well. I am afraid, though, that the larger pipe means that the same amount of air is flowing slower out the nozzle than it did before.
Oh, so because we're moving only this much air, it's not going to go as fast because this is a bigger tube.
We need a bigger volume over here to match our larger
So a
nozzle.
bigger bottle.
That's right.
I got a bigger bottle right here. Ha-ha! Bigger bottle! So hold that, and then all we have to do is tape the bigger bottle
I'm not sure
on.
if that's gonna...
Yeah, like this.
Still, though, I'm crazy.
Yeah, so then all I need to do is tape it on. Chris and I attach a larger bottle to our tube. We just need some risers to adjust the height, then we tape it on and we're good to go. Everything else, including the rocket, stays the same.
I still don't understand how you're gonna step on this one. It's just too stiff.
I have a plan. Ha 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 ha! Sledgehammer! You ready?
Yeah, I'm ready.
Okay. 1, 2, 3! It blew the top off the rocket.
Right off
it
the
also
top.
blew the bottom.
Looks like it's a bit rigid to change its volume so quickly.
So it's kind of a one-time use thing, huh?
I think so.
So why don't we try increasing the volume? Even bigger tube,
Yeah.
even bigger container.
What's bigger than a... That's the biggest bottle they make.
What else holds air?
What about an air mattress?
Do you think we could use an air mattress?
I think we could, yeah. A really big air mattress.
Oh, totally. High five. I love that idea. Moving air is a lot of fun, especially if you use one of these, a vortex cannon. They're pretty impressive and they use some pretty amazing science. I'll show you how to build one. It's pretty simple. All you need is a plastic cup, you want a balloon, something round, an elastic, scissors or a craft knife, and a pen. Here's what you do. Take your balloon and cut it just where it gets wide. You take the mouth of the cup right there, and you have to stretch the balloon over the top. And then you want to put an elastic around it, keep it in place. And this now is a surface on the top, and that's what you're going to use to pull back and create your burst of air. But of course, the air's not going to go anywhere until you make a hole in the bottom. So here's what you do. You take your round thing and draw a circle, and take your craft knife or scissors and an adult and get them to help you cut out a hole. And when you pull back on the balloon, a burst of air comes through the hole. But the air has an interesting shape. Now, I know what you're thinking. You're thinking, Phil, air is invisible. You can't tell what shape it is. Well, I can show you. Come on. This is my maxed out vortex cannon. It's made out of a garbage can. I've got a hole in here, and this is a shower curtain with a ball that I can get a grip on and pull. And then it shoots forward like this. Now, it makes a big puff of air, but again, the air is invisible, so we don't know what shape it is, but I can help with that because I've got this, a fog machine. I fill the inside of the garbage can so we can see what the air is doing when I fire the vortex cannon. Okay, come on over here. Ready?
Whoa! Okay, ready? Check it out.
The vortex cannon shapes the air into a ring, called a vortex.
It makes a ring. Well, actually sort of a donut.
Because of its shape, the air in a vortex can move much farther than air that doesn't have a shape.
Vortex cannon. Air that has a shape goes a lot further than air that doesn't have a shape. And it's also way more fun. Woohoo! Little to the left. Little to the left, Ramona. Okay, now that's too far left. I don't know what you think. Oh, hey, I don't suppose you're going on vacation anytime soon. Well, if you haven't decided where, may I suggest underwater. But don't forget to pack the most important thing when you go. Hat? Nah. Ukulele? Nah, forget about it. Rubber chicken? No. Sunscreen? Forget about it. Teddy? No, if you're going underwater, the most important thing you gotta pack is air. You see, human beings have been coming up with ways to go underwater for a long time, but the thing is, you gotta bring air with you because, you know, breathing is good. Check this out. It's a diving bell. One of the first ways humans used to be able to take air with them when they went underwater. You see, it's a big, heavy bell, and it's lowered from a ship above on a rope. And when it gets lowered into the water, it traps a bubble of air underneath. So you can swim around underwater, but then when you need to breathe again, you don't have to go all the way back up. You just pop under the bell and take another breath. Bells like this were actually much bigger when they used to use them for diving to hold more air. Huh? Ring-a-ding-ding. What do you think? You want this? No? It's okay. I got something else. Hold on. Check this out. It's an old-timey diving suit. Air is pumped in through these hoses here, which means the diver has a constant supply of air, which means he can stay underwater longer. What do you think? No? Okay, hold on. I got something else. Yeah. This is it. The ultimate in bringing air with you. The scuba suit. This tank holds compressed air, which means it can carry a lot of air with you, which means you can stay underwater for longer. So I'll tell you what, I'll wrap up all three things. What do you say? Yeah? You'll take them? Okay, great. Let me just wrap them up for you. Come on, Teddy, let's go find the bag.
So our large stomp rocket hasn't worked perfectly. A small bottle didn't move enough air, but our larger bottle was too rigid to stomp. And when I used a sledgehammer, it was so sudden the bottle broke and also blew apart the rocket. Chris and I need a large container of air that is soft enough to change its shape easily. So here's the current plan. An even larger pipe, an even larger rocket, and we use an air mattress. We make two holes in the air mattress, one to fill it up with a leaf blower, and the other hole to go out the tube to the rocket. Since an air mattress holds lots of air and is very easy to change the shape by jumping on it, we figure it'll be a great way to get lots of air through the tube to launch our rocket.
Okay, let's do it.
Let's do it.
All right, we're gonna go 1, 2, 3, jump, right?
Okay, yeah.
1, 2, 3.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello! Welcome to Cooking with Science. I'm Buster Beaker. Whenever friends come over, I like to make my famous potato chip recipe. And look at this bag of potato chips. Quite large, there must be a lot of potato chips in here, right? Well, let's open it. What? This potato chip bag is mostly air. Why do potato chip bags have so much air? Well, to tell you the answer to that, I have to tell you the story of 2 bags of potato chips. Here they are. This one full of air, and this bag of potato chips, there's not much air in it at all. Why don't they make them like this? Well, let's find out.
first thing that happens is the potato chip bags come off the conveyor belt at the potato chip factory where they get packed into a crate. Here's a crate here. So let's really stuff them in. And then the crate gets boxed up and shipped off to the store. Oh, it's a bumpy ride to the store today. Now we're at the store, and then you come along. Ah, bags of potato chips. What else should I buy today? Oh, I know. How about a cantaloupe? Very nice. Some apples, yes? And take it home, walk along, and you get to the kitchen. You have a choice. This bag of potato chips, where all the potato chips are light and fluffy, or this bag of potato chips, which is not exciting at all. And that's why potato chip bags have so much air, to protect the potato chips from getting crushed. Speaking of potato chips, time to get back to my recipe. What is it? It's potato chip soup. Well, I'm Master Beaker, and thanks for joining me on Cooking with Science. Perhaps a little bit more cooking.
Okay, so where were we? Oh, right, our maxed out rocket. A much larger pipe, a large air mattress, and the largest rocket yet. Let's see how it goes.
1, 2, 3, jump. 1, 2, 3.
Yeah! There you go.
All right, let's do it again. Okay. 1, 2, 3.
It works amazingly well. The large volume of air Chris and I can move by both jumping on the air mattress gets transferred through the large pipe, and even though it's a giant rocket, it sails higher than any other version.
That was great. That was amazing. All right. There you go. Science Max, experiments at large, moving a lot of air.
That has to be the biggest stomp rocket ever.
Biggest stomp rocket ever. Let's do it again.
Okay.
Okay.
Oh, it smells so horrible.
It's a diving bell.
And that didn't work at all.
That's acting, my friends. Oh, friends, it's so bad.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. Yeah! My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! This episode of Science Max is a messy one. We're looking at solids, liquids, and gases, and things in between, like cornstarch mud. Today on Science Max, experiments at large.
Behold the power of states of matter! Greetings, Science Maximites!
I'm Phil McCordick. I think I overdid it with the fog machine. This is Science Max, experiments at large. Can you even see me? Let's go over here. Today we're talking about states of matter. Now there are 3 main states of matter. Solid, like this table, liquid, like the water in this beaker, and gas. Yes, thank you. And we're also going to be looking at the things that kind of go in between. Things that are sometimes solid, sometimes liquid, like cornstarch mud, which is very easy to make. All you need is water and cornstarch, which you can get at the grocery store. Mix it up however much you want. Just remember, 2 parts cornstarch to 1 part water. Twice as much of this than you have of that. Very easy. Mix it up and you get cornstarch mud, which sort of seems like a liquid unless you hit it. And then it becomes solid. But if I pour it, it's a liquid. Even if I hold it in my hand and I hit it really fast, it turns into a ball, and it will stay in a ball as long as I keep hitting it or squeezing it. But as soon as I stop, it turns into a liquid again. Now we're gonna max this out. We'll go through the portal and learn more about solids, liquids, and gases.
Yeah, right.
That's why I'm going to the Center for Skills Development and Training. Oh, no, wait, that's the code for the fog machine. Wait, stop. Stop. It seems to be stuck. Oh, never mind. I'll fix it later. Right. Hey, Judy, how are you?
Hi, Phil. How are you?
Good. Judy is going for her PhD in chemistry, right?
Yes.
Fantastic, because that means you can explain cornstarch mud to me. Now, is this a solid or is it a liquid?
Well, it kind of has properties of both. It's called a non-Newtonian fluid,
Uh-huh.
so that makes it a liquid.
A liquid? Well, I mean, it pours like a liquid, but when you hit it, it's a solid. So why does it turn solid when you hit it?
So when you're pouring it, the particles are still far apart, so they can't interact with each other, and so they stay a liquid. But when you're hitting it, you're jamming the particles together, and they line up to become a solid.
Now, does it still work the same way if we have a lot more of it?
It should.
Great, because I've got this 20-kilogram bag of cornstarch, and I have 34 more of them.
Wow, that's a lot. But I think you'll need a much bigger container.
Much bigger container. Great. I got some wood over there. Why don't you go, and I'll follow you.
All right.
I'll follow you. I'm coming. Yeah, thanks, Ramona. And give me one of them fizzy drinks. Not too fizzy, just sort of medium fizzy. Thanks a lot. Hello, do you have trouble knowing what is a solid, liquid, or gas? Are you confused by Jell-O? I mean, which is it? Is it a solid or is it a liquid? Water is a liquid, but what about when it's ice? Well, you gotta know your states of matter. There are three main states of matter: solid, liquid, and gas. And there are three rules that you need to figure out which one of them is which. Does it flow? Does it fit the shape of its container? And can you squeeze it? Rule number one, does it flow? Solid, liquid, gas. Here's a gas. Does it flow? Do the particles pour over each other and cascade down? Yeah, they do. Does a liquid flow? Yeah, it does. Does a solid? Nope. Rule number two, what happens when you put it in a container? Does it take the shape of the container? Gases take the shape of the container. Liquids takes the shape of the container. Solids do not take the shape of their container. I know what you're thinking. You're thinking, I get the whole pouring and taking the shape of the container, but come on. Liquids and gases, they do both of those things. Well, it all comes down to rule number three. Can you squeeze it? Now, solids, you can't really squeeze them. Liquids, you can't really squeeze them. Gases, bam, you can squeeze them. You see, gases compress. Liquids and solids, they don't really compress very well. The other difference between gases and liquids is gases will take the shape and the volume of the container they're put in. Liquids don't do that. So there you go. Solid, liquid, gas. And the rules. Does it flow? Does it take the shape of the container? And can you squeeze it? Now you know your states of matter. That'll be $6.50. Cash only.
So what is cornstarch mud and how does it work? Well, cornstarch mud is a non-Newtonian fluid, which means it behaves differently than you, or Newton, would expect. Here's cornstarch, and here's water. Cornstarch is made up of large, blocky molecules like this. Water is made up of much smaller, rounder molecules like this. When you put them together, it looks something like this. It all has to do with how the molecules slide past each other. When you put light pressure or slow pressure on the mud, the water molecules and cornstarch molecules have time to shift out of the way. But when you put a sudden pressure on it, the water molecules squirt out of the way, but the cornstarch molecules don't have enough time. So you get a section that's nearly all cornstarch, which acts as a solid. Cornstarch mud is a shear thickening fluid. Shear is talking about the force of things sliding around, in this case, the molecules. So when the shear force is strong, the fluid thickens. Shear thickening. So here's the plan. If Judy and I make enough cornstarch mud, could we run across it? Let's find out.
Yeah, I think mine is just the right consistency. How's yours, Judy?
I think I'm ready too. This is much harder than I thought.
Yeah, it's really hard to get it mixed at the very beginning, but mine is ready to go. Okay, here we go. First batch. You ready?
Yep.
Dump it in. Woo! Woo! I thought that would be more.
I thought so too.
It's really not filling this up very much, is it?
No.
Huh, that's a lot of cornstarch. This is great, but I think we're gonna have to go a little faster than this.
I think we need some sort of mixing device.
Yeah, I mean, we don't have to do this by hand. We can get some sort of machine to help us.
Yeah.
Right on, high five.
Oh.
We shouldn't high five when we have this stuff on our hands.
Nope.
Yeah, good call. This science is delicious. This is rock candy. It's basically crystallized sugar, and you make it by turning a solid into a liquid and then back to a solid again. Here's how you can make it at home. You need a container that you're not gonna need for a while, and some water, some sugar. You can use brown or white. I like to use brown. And an adult. Here's why you need an adult. You want to dissolve 3 cups of sugar into every cup of water. And you can't do that unless you heat the water. So get an adult, a saucepan, and heat the water up, pour the sugar in, and keep stirring until it's all dissolved. Then pour it in your container and let it cool down. Then you'll need a shish kebab skewer, which is something you can get at the grocery store. Cut it down to the right size so it fits nicely into your container. And then dunk it in your sugar and get some crystals coated around the stick. These are seed crystals, and they get the whole process started. And now you have to wait for these to dry, otherwise they'll just fall off the stick when you put it in the water. So I've got one here that has dried out. You'll also want something to keep it from falling in the top of the container, so I'm gonna use a clothespin. Put it in there and dunk it in the container like that. And now for the final step, if you want, you can add food coloring. I like to use red because it reminds me of science. And I'm gonna use the stick to actually stir that up a little bit. There we go. Now, the dissolved sugar crystals in the water will slowly grow on the crystals that are already attached to the stick, and it will eventually grow into a rock candy pop. But it takes about a week. No, I'm just kidding. I've already got one that's standing by. Here we go. This one has been growing for about 7 days. And there you go, rock candy. Delicious science. Now, how can we make this any better? I mean, it's crystallized sugar. It doesn't get any more maxed out than that, does it? Yeah, it does. Come on. This is a giant container of sugar water, and I've been brewing a massive rock candy crystal in it for a while, but it's sort of getting a little bit too big to fit out the top of the container, so you know what? I'm just gonna put that back in there and chalk that one up to science because, well, eating a rock candy crystal that big will definitely not be good for my teeth, so yeah.
So our big experiment is to take a whole lot of cornstarch and fill a trough to see if we can run on it. But mixing it by hand was going to take forever. So Judy and I got a drill with a mixing attachment on the end.
Whoa, sorry. All right, so Judy, I'm noticing a bit of a problem here.
What is it?
Well, if I mix at the top, everything's fine. But as soon as I get it a little bit deeper, and then it gets really tough, and the whole bucket starts to spin, and the drill stops.
Yeah, I think it's because the drill's trying to mix it too fast. When we're mixing it by hand, it's slow, and you can still let it stay a liquid, but now you're just making it a solid.
Right, because it's a shear thickening fluid,
Exactly.
so if you hit it really quickly with something, like the blades of this spinning really quickly in the thing, it'll suddenly turn into a solid, and it'll be really hard to mix.
Yep.
So we go slow. Going slow. Going slow. Suddenly realizing that if we go slow, we'll be here forever.
Yep.
You know what I think we need? Whoa, sorry. You know what I think we need? We need a different way to mix this.
Yep.
We need a way to mix more of it, and we need a way that it doesn't hit it with blades that suddenly go through it really quickly?
Something that can mix on a large scale, but slowly.
I have just the thing. Come with me.
All right.
The interesting thing about bubbles is they're a gas surrounded by a liquid. So get some dish soap and some water, and then be Science Maximites and find things around the house that you can make bubbles out of. Just about anything that has holes will do. Or I like this one. I call it the loud bubble. Or now it's time to max it out. I'm here at the Ontario Science Centre, and this is Anthony. Hey, Anthony.
Hey, how's it going?
Good. So you are amazing at bubbles.
I am. I've been practicing for a while. Let's get started.
Okay.
You're gonna make an okie dokie sign like this.
Uh-huh.
You're gonna dip it right into our bubble solution. Come on, get right in there, right in there. Make sure you get it all. Oh, that's a little too much.
Well,
That's
then I
good.
can make two.
And then you're gonna keep that okie dokie sign. You're gonna blow very gently.
Nice.
I brought these two giant sticks here, and I don't know if you noticed, but I've got a smoke machine here.
Right.
So we'll turn that on, and then if you press that green button there, you're gonna shoot some smoke, and we're gonna try to catch that smoke in a giant bubble. You ready? Okay, and I'm gonna try to... Oh, that was so close. Did you see that one? You give it a shot. Nice! Oh, check that out! That's amazing! That was huge. Try it again. Let's see if I can get the smoke machine. Here we go. Go for it, go for it. Push right towards. Oh, check that out! You did it! Look at that! Look at that! No! Smoke, and it bounces on the floor because the floor, it doesn't have any oils like our hands do. Isn't that amazing?
That was
oh
great.
my God, that was so cool.
That was great. You know what I think we should do?
What's that?
Giant bubble, tons of smoke.
Done.
Okay, here we go.
Let's do it. You ready?
Giant bubble, tons of smoke. Go.
Awesome! Oh my God! Look at that! Amazing! Look at that! That's crazy!
Max out bubble. Well, there you go. Giant smoke-filled bubbles.
Awesome!
Yeah! Judy and I tried mixing the cornstarch mud using a drill with a mixer attachment, but it didn't work. We should have known better. Here's the mixer in our cornstarch mud. Usually, a mixer works by going really fast and mixing everything together. But remember that cornstarch mud is a shear thickening fluid. So, when the blades of the mixer tried to go fast through the cornstarch mud, it did what it always does, turn solid. The faster and harder you try to move it, the more solid it will become. This means the only way to mix it would be if we made the drill go very, very slow, which wouldn't speed things up at all. So with the drill another lost cause, Judy and I need the biggest thing around that could mix stuff up.
Come on back. Good.
Little bit more.
Perfect. A cement truck is the perfect thing to mix because all we have to do is get all the cornstarch up in here and it'll mix it and it doesn't move it too fast. It goes nice and slow, so hopefully a shear thickening fluid will be fine. I'm gonna get Judy. She's driving the truck. Hey, Judy, that's perfect.
The only problem is we needed to get all of those bags of cornstarch into the hopper of the cement truck.
I didn't think it'd be this messy.
We needed to call the entire Science Max build team to help us out.
This is possibly the messiest thing I've ever done. Awesome! Woo! Hey, Judy, you wanna lift up any bags?
I'm okay, thanks.
That's okay. I'm having a lot of fun, so I can do them.
Cool.
Oh no! Oh no! Oh no! Yeah! I got most of it. All right,
I think we're done. I think that's enough bags. Let's start the mixing! So, what do you think, Judy? Do you think it's gonna work?
I think so, because you're mixing at a very large volume, but at a very low speed.
Yep.
So throughout the process, it'll stay a liquid until we're ready to run across it.
That sounds exactly like the kind of science I like to see. You know what I really like is that every time I move, more cornstarch comes off. It's like I'm a human fog machine. This is liquid nitrogen. Nitrogen makes up most of the air we breathe, but if you get it really, really cold, it turns into a liquid. The fun thing is you can use it to make other things really, really cold too, like this banana. I have frozen this banana solid thanks to the liquid nitrogen, and normally a mushy banana would not be able to hammer in a nail, but whoa, because it's frozen, I can hammer this nail into this block of wood. So that got me wondering, if I can turn a banana into a hammer using liquid nitrogen, could I turn a pumpkin into a sledgehammer? Let's find out. Pumpkin sledgehammer, take one. No, I think the answer is no. You cannot turn a pumpkin into a sledgehammer with liquid nitrogen. All you can do is make a really, really big mess. I'm gonna have to clean this up, aren't I?
Now we have a cement truck to help us do the mixing for our cornstarch mud. After making a giant mess getting the cornstarch into the cement truck, it's time to see if it worked.
Hey, Phil, how's it going?
Yeah, it looks like it's mixing pretty well. I'm really glad we're not doing this by hand, because it'd take a really long time. We've almost got it at the right consistency, but it's taken some time. But it's getting a little dark out, Judy. I don't know, do you want to quit and go home?
No.
Of course not. That's not what we do in science. Oh, here we go. Yeah!
Awesome.
All right, let's see it. Let's see if it's... I like how it comes down in little steps. And look, it's working just like it should. I hit it, and it's solid, but you can see it's pouring like a liquid. Yeah, here comes a big wave.
Wow.
Here it comes. Oh!
And it's totally filling up.
Oh yeah, filling up really fast. I think we should stop pouring very soon.
Yep, we may not have a big enough trough. Yep.
Liking it.
It's good.
Yeah. I think it's time. It's not even done pouring, but I'm gonna try it. Okay, you ready? Whoa.
Oh, and you did it!
Whoa. You have to get back onto the sides before you stop moving.
Or else it becomes a liquid.
All right, it's your turn.
Okay.
Here.
Go.
Okay, ready?
Okay.
You gotta hit your feet really fast.
All right.
Here, go.
Yeah! This actually works.
Because cornstarch mud is a sheer thickening fluid, it means it stays a liquid until you hit it suddenly, like with your hands, or in this case, our feet. And then it turns to a solid. So as long as Judy and I keep slapping our feet down with enough force, we can walk on top of it.
One more dance.
All right.
And
let's
tell you
do
what,
it.
we'll do one more dance.
All right, let's do that.
Okay, ready?
All right.
And go. All right.
All right.
Yeah, there you go.
We've done it.
Solids, liquid gases. Thanks very much for joining us on Science Max Experiments at Large. Woo! Hey, Judy, catch. I have to be careful because the banana will shatter if I'm not careful. I think it's stuck on the bottom. I call this one the loud bubble. Oh, well. I call this one the loud bubble. I don't think I can do it.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Today, I'm maxing out the power of water.
Water is very heavy.
Pressurizing water to make a water-powered car, water pressure pumpkin carving, water flying, and more. All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're gonna be looking at water, but water is very heavy. But that's okay, because we need it to be heavy for this experiment to work. I don't know if I need that much of it, though. Maybe I can get, here we go. Yeah, that's probably all I need. Today, we're going to be building a water-powered car.
You'll need a base for your car, like this styrofoam, water bottles, shish kebab skewers, straws, scissors, elastics, paper plates, tape, a square of paper towel, modeling clay, vinegar, baking soda, water, and glue or a hot glue gun if you have an adult to help you, and... yeah, I know, this one is pretty involved. That's why you should go to the website for step-by-step instructions. Take your paper plates and glue 2 together to make a wheel. Then make 3 more. Wrap elastics around your base and then tape straws on the bottom.
Trim them down, maybe about that much.
Then take your shish kebab skewers and push it through a water bottle cap to make a hole. Then stick one wheel on, put the skewer through the straw, and
do the same thing on the other 3 sides.
Then take the water bottle cap and get an adult to help you make a perfect hole in it so that it fits your straw. Then use some modeling clay and hot glue to seal the straw and the cap so it's airtight. Attach the water bottle to the base of your car, then fill it with some water and vinegar. Next, you'll want to wrap up a spoonful of baking soda in the square of paper towel so you can make a little package. Finally, stick something underneath the underside of the bottle to raise the end up off the base.
Bring your cap and then go outside. Here we are outside. Yeah, I know, we're not really outside, but I have a science lab and you probably don't, so I highly recommend you do this outside.
And don't forget your safety glasses.
Now, this is why we make a little packet of baking soda, because we want to delay this reaction as long as we can. So I like to hold it there. We'll hold it there with one finger so I can get the cap ready, because we don't want it to react until we can get the cap on, and then kink the straw to keep the pressure inside till we're ready to let it go. Then, at the last second, you want to drop that packet in and quickly cap it, and kink the straw, and woohoo! Woohoo! There you go, a water-powered car. Now, I know what you're thinking. You're thinking, Phil, wait a minute, that's a vinegar and baking soda-powered car. Well, kind of. The vinegar and baking soda create a gas, and that gas creates pressure in the bottle, and that pressure forces the water out of the bottle. But it's the water leaving the bottle that creates the thrust. The water going that way pushes the car that way. Newton's third law, every action has an equal and opposite reaction. So what we're gonna do is max out the water-powered car. Figure out how to get water going that way so we can go that way. But we means me and someone else. Who can help me? Oh, I know, Anthony from the Ontario Science Centre. He'd be great at this. Hopefully he's not busy. We're gonna max out the water-powered car. Ha. Anthony! Phil, sorry about that. Did I scare you?
Don't worry about it.
How you doing?
Awesome, thanks.
Great. I was wondering if I could get your help on an experiment.
Yeah, okay. Which one?
I'm building a water-powered car. It's gonna be great. It's Science Max headquarters. I'll show you.
Phil?
Anthony, I'm here.
Whoa. Phil, where are we?
Oh, this is the parking lot for Science Max headquarters. So,
okay.
Today, I want to max out the water car.
This thing is awesome.
Yeah, so what you do is you use vinegar and baking soda, and you pressurize this container.
Okay.
And the